an introduction to the UK-ASEAN Energy Efficiency Accelerator, which is our program working in the food and beverage sector in this region on energy efficiency. Kalyani, over to you.
Thanks, Eloise. So just a bit of background to start off with on Carbon Trust. So we were established in 2001 with the goal of accelerating the transition towards a sustainable low carbon economy. So we provide a range of advisory services to business, government, and multilateral organizations. And this ranges from climate policy advice, assurance and certification of an organization or product's carbon footprint, corporate advisory on setting sustainability targets, program design, technology innovation advice and assessment, and also green finance services. Next slide, please. So the ASEAN Low Carbon Energy Program is funded by the UK government, and this aims to address some of the key barriers in the energy sector by catalyzing energy efficiency and also improving green finance flows in the region. So we are partnered with Ernst & Young and IMC Worldwide to deliver this program, and Carbon Trust is leading on the energy efficiency component across 5 key countries. So these are Malaysia, Myanmar, Thailand, Philippines, and Vietnam. And so we're focusing mainly on providing energy efficiency policy support, capacity building on energy efficiency for governments and business, providing technical assistance to project developers, and also improving energy efficiency product standards in these countries. Next slide, please. So the UK-ASEAN Energy Efficiency Accelerator is one of our key programs under the LCEP and focuses only on the food and beverage sector. So under this accelerator, we are supporting F&B companies to improve their energy management, promote the adoption of energy efficiency, and also set more ambitious energy performance targets. And all of this support is provided at no cost to companies. The key types of support that we are offering under this accelerator include online tools and guidance resources, and all of these are publicly accessible to you. And I will provide you with a few examples shortly on this. We are also delivering regional and in-country workshops on energy management and energy efficiency best practice. And finally, we are offering one-to-one tailored assistance to a handful of companies on specific areas where they require more support related to energy efficiency. Next slide, please. So I will now take some time to go over some of our resources available on our website. And I have just dropped a link to these resources. So while I speak about all of our tools, please feel free to go on this link and explore the resources that we have available. So we have a couple of energy savings guides that focus on 7 of the most common processes in the food and beverage sector. So these cover case studies and international best practice on energy efficiency measures. And we also have energy management guides and tools. So if you are new to energy management or are keen to improve your existing energy management systems, then we highly recommend our guide to establishing energy management systems that are aligned to ISO 50001. And we also have 3 self-assessment tools that I will quickly walk through now. So the first one we have here, so this is a snapshot of our energy management matrix tool that offers you a very high-level assessment of your company's progress in energy management. So all you would need to do is score your company based on what describes your development against key factors related to energy management. And you will get a visual representation of areas that you can improve upon. And this can eventually be presented to senior management for any further action. So this is a great tool to use if you're new to thinking about energy management. The next slide, please. So this is a snapshot of our second energy management tool that offers a much more comprehensive assessment of how you measure against energy management best practice. So this tool goes into much more detail on 12 of the key categories behind a successful energy management system and describes the characteristics or components that these should include. So all you would have to do is score your company based on our scoring guidance for each of these characteristics. And the output is the diagram on the right, which demonstrates your strengths, weaknesses, and where you would benefit to focus your efforts more on. Next slide, please. So this is the final tool that we have. It is a top 10 energy efficiency checklist that we have developed for 7 of the most common processes used in the food and beverage sector. So here we have an example of our tool for steam systems. So you would just need to input into the yellow cells where you select the fuel type used by your steam system, the currency of your choice, your annual fuel expenditure, and estimated percentage use by your site of the system. And then you would just have to answer whether or not you meet the best practice criteria that is highlighted here for your system. So if you are aligned, then the tool gives you feedback as to how much costs you are saving and the emissions that you are reducing. And if you are not aligned, then you get feedback as to how you could improve your system and its corresponding energy and cost savings, as well as an estimated payback period. So feel free to use these resources on our website and reach out to us if there are any questions or requests for any other forms of guidance. I will now hand over to Karthik, who will talk about our technical assistance offerings under this program.
Thank you, Kalyani. Good afternoon, everyone. I'll start off by talking about the technical offerings under the program. So the program offers a one-on-one technical assistance, starting off with helping companies to conduct energy audits, be it virtual energy surveys or a full-blown detailed and on-site energy audit, depending on the needs of the company. We also help companies to identify and scope up energy efficiency projects by starting off with a techno-commercial feasibility study and talking about commercially viable projects, quantifying their potential energy savings, and even helping with the implementation roadmap as well as the energy efficiency financing options that are available. We also want to help companies on setting up a structured energy management system, assisting them to establish a new structured energy management system or upgrade their existing energy management system in line with best practice, which is ISO 50001. Similar to this, we are also conducting internal capacity building workshops on this is more on company specific workshops, so identifying energy saving opportunities, preparing the business case for these projects in line with the techno-commercial feasibility studies that we have previously conducted, and also providing guidance to internal stakeholders within the organization on how to operate successfully, the structured energy management system, so that it is a continually improving system that is on place. We also help companies on setting targets, energy strategies and energy targets, and feeding into the overall organization science-based targets. And where there is a need, we also help in brokering or matchmaking energy efficiency solutions with the appropriate needs. So be it costing, liaising with vendors and so on. Next slide.
If we could just launch our first poll, Karthik, on this slide. So we're really interested to know from this list on your for your organization, which would you find the most useful? Which one is the one that you feel that as an organization you feel that you would most benefit from? So I'm going to launch a poll, and if you could just take a 30 seconds to vote on the solution which you find the most useful, and then right here on the screen we will all see the results. So please take a moment to answer the question that's on your screen. Thank you. I can see answers flying through to me. So keep making your choices. I'll give you 20 more seconds. 10 more seconds. Any final votes that want to be put forward, that'd be fantastic. Great. Well, thank you all for those that voted. I will now put on the screen the results. So interestingly, hopefully you can now all see the poll results. Across the board, there is responses, but it's the identifying energy efficiency project which has come out on top with nearly 35% of the votes. So that's very interesting for us, and it shows that there is a willing to act on energy efficiency, and potentially not the understanding on how to formulate and bring forward projects forward. And we will take that on board in terms of engaging further on this program. So thank you. Yeah. Karthik.
Thanks, Eloise. Yeah, these the top three are energy auditing, identifying opportunities, and setting up energy management system. In fact, the services have been outlined here in this slide in order of early on to more mature, kind of progressive in that way. So it's very understandable that these three are the top preferred service offerings. So if you can move on to the next slide. So here we'll be talking about a snapshot of the food and beverage sector in Southeast Asia in the 5 targeted countries that we are working with. So we see that food and beverage companies are an important economic driver, specifically in Thailand. They contribute to about 20-22% of the GDP, and followed closely by Philippines and Vietnam, just shy under 10%. So it also shows that in Myanmar, which is it's at its early stage, but of course there's a huge growth potential for food and beverage sector in this country. And energy efficiency becomes a critical need as the industry develops. So energy saving measures and reducing carbon emissions will form critical requirements so as to drive profitability as well, so as to drive an inclusive growth. You can move on to the next slide. So here we are talking about, we are deep diving into the breakdown of the energy mix, across the various countries that we have worked with. So as you can see, electricity makes up quite a small percentage of the energy mix in the food and beverage sector. In many of the companies that we have conducted, food and beverage companies that we have conducted an audit in, electricity just makes up about 20-30% of the total energy consumption. Majority of the energy requirement is thermal in nature. So we will see the reasons for that owing to the processes and all that. So in Malaysia, much of this thermal energy is delivered by natural gas, availability of piped natural gas. But in the other countries, especially in Thailand, we see a lot of biogas and biofuels and waste-derived fuels being used. And also notable that in some of the food processing facilities, wastewater treatment plants, you have anaerobic digesters. So the biogas from some of the plants that we have worked with almost substantially meets the thermal energy requirements of these plants in Thailand. So if we can move on to the next slide. So here we are talking about the typical processes. I'm sure you're familiar with the various processes involved. Starts off with feedstock preparation, size reduction, various separation processes, and other processing operations such as fermentation, coagulation, solubilization, and heat-derived processes, and concentration by drying and evaporation predominantly, and eventually removal of heat for either freezing or packaging operations, and eventually packaging and filling operations and the associated utilities. So as you can see in these process makeup, much of the energy consumption is happening in the separation processes, in the various heat processing operations, baking, drying, pasteurization, sterilization, as well as in the concentration processes, which include drying. These are the processes that contribute to much of the energy consumption. And all of them are thermally driven processes, and hence you can see that thermal energy constitutes a significant part of the energy mix of the food and beverage processing plants. And on the right hand side, I don't want to delve deep into this. These are the various energy systems that you can typically find in a food and beverage processing plant. And if we can move on to the next slide. So here we are talking about potential for energy saving. So in the various countries where food and beverage sector plays a significant economic role, the energy savings potential in the food and beverage sector is actually determined by comparing the current energy intensive processes in place in these sectors and the technologies used by companies that we have studied, in comparison against the best available processes and best available technologies in the market. So that's how we arrived at this potential energy saving opportunity. So you can see that there's a significant opportunity to save energy in the food and beverage sector in Thailand and Vietnam. Yeah, specifically in Vietnam from the seafood processing sector. Yeah, you can move on to the next slide. So in this slide, what we are looking at is a holistic energy management journey, and it gets increasingly progressive as you move from left to right. Starting off with energy management, I'm not going to go into each of these blocks, but let's focus on energy management for now. So we're talking about measuring and monitoring savings, understanding what is the energy makeup like, what are the significant energy uses that are measured, what needs to be measured. And so that distills down to seeking expert advice on establishing a structured energy management system in place, identifying the pipeline of energy efficiency implementations that need to be put in place, and then prioritizing them based on the approximated energy savings as well as the cost associated with those energy efficiency opportunities, and then also getting a holistic understanding of how to improve the measurement plan within the facility. And then we move to distilling down into the actual energy saving opportunities that can be implemented. They're developing the implementation plan. And on the left-hand side of the blue box, there are two blue boxes. On the left-hand side, we're talking about energy conservation, so minimizing wastage. So addressing suboptimal operational parameters, adjusting excess O2 in the furnace or boilers, optimizing steam letdowns, reducing overcirculation of pumps, minimizing or avoiding fugitive leaks and emissions. And on the right-hand side of the blue box, we're talking about implementing energy efficiency technologies, such as maybe economizers, air preheaters, and such a high capex items. And if you move, once the energy efficiency potential has been realized, has been maximized, then we move on to further greening the energy mix by looking at renewable energy options, evaluating on-site renewable energy options, identifying or studying suitable technologies that can be used, taking into account budget and technical considerations. And once that renewable energy potential is also exhausted, then the journey towards carbon neutrality is then identifying or procuring renewable energy certificates to offset the outstanding energy consumption. So I think there is a timely poll now. I didn't miss it this time.
Thanks, Kartik. So moving on to our second poll of presentation, we just want to gauge a little bit about where you think you are as an organization on your energy management journey. And so it's a fairly simple question where we're just asking you, where is your organization in terms of energy management? Do you actively manage and try to reduce your energy use? No pressure on the answer. Obviously, please be honest. I think that's the most important part. And obviously, it's a really good indicator for us on where we need to position our information and how we can support food and beverage companies and other companies in this region. So please do vote, and I'll give you 20 seconds to cast your vote on this one. Ten more seconds. So if you could just put forward your vote, it'd be great. I can still see people voting, so I'm just going to leave it 5 more seconds. If you just cast your final votes, that'd be fantastic. There we go. Okay, great. So I will show you the outcome of that vote. So obviously the results encouraging. You know, 58% of you are really actively managing energy, and it really is an established company activity. But there are people, are organizations listening in, and that this is something new or is something that's not quite a priority for your organization. So yeah, we will take that on board, and I suppose it's interesting for you to see what your peers are up to as well. So thank you for your vote, and we will move on. There's the results there. Yeah. Great. Thanks.
Yeah. Thanks, Louise. Yeah, it's timely. The results are right. Yes, majority of the companies mentioned that this is an established company activity, rightly so. Energy management, as you can see, is at the leftmost part of this. It's a low-hanging fruit that needs to be addressed. The thing about low-hanging fruits is that they always tend to grow back. So it's always very immediate things, the first things that need to be addressed. And for respondents who mentioned that yes, this is a new subject, or no, we are planning to start managing soon. So this is where this whole program is geared at, targeting at companies like yourself. And for companies who believe that this is not a priority item, maybe I hope that the next slide would help to convince you. Yeah. So structured energy management system, and just like any other management system, follows a PDCA, plan, do, check, act cycle. Drives a continuous improvement. I'm sure many of these improvement points here are something that is very well familiar with you guys, with the audience here. So definitely it provides you a structured approach, a library of library of processes that you can check against. That's what energy management system provides. It enhances the resource efficiency, overall resource efficiency of your organization. Definitely bottom line savings, and in line with your organization's drive towards decarbonization and reduced emissions of greenhouse gases. In some countries, such as in Singapore, there is a legislation which says there is a need for a structured energy management system to be implemented by significant energy use companies. Yeah. And also it generates increased organizational awareness. It drives down to all your internal stakeholders, your employees, that at organization level, there's a drive towards sustainability and energy efficiency, and enhances reputation amongst your consumers. And increasingly, it becomes either a mandatory or a critical evaluation point in a lot of tenders. Yeah. You move on to the next slide. So in line with the sharing session today, there are various energy systems within the food and beverage industry. So we wanted to just focus on one industry, so that it will flow nicely with the next set of presentation we have from our partner company. I mean, Spirax-Sarco later on. So it's with optimizing energy use in boilers. As we have seen previously, boilers provide the thermal energy that is a significant driver for much of the processes in the food and beverage industry. So if you can see that efficient boiler operation and efficient steam distribution system saves around 10 to 30% of the energy consumption. So we're talking about optimal loading of boilers, distribution systems with effective insulations in place, appropriately functioning steam traps, and then appropriate condensate recovery system in place. And we are talking about, in the next step, we're talking about having combustion control mechanisms, a burner management system, O2 trimmers, and combustion analyzers. And these could easily save up to 10 to 15% of your energy saving. And 10% of energy can be actually, typically 10% of the heat is lost through ineffective insulations. And majority of this can be saved by using cost-effective insulation material and periodic steam surveys to measure insulation heat loss. 4 to 6% roughly can be saved by installing economizer to reduce stack temperature and use some of the waste heat. So I think I'm done with my set of slides. I will pass on to the next set of presentation, which talks about steam system fundamentals.
Thank you, Kartik. So yeah, thank you for, hopefully that covers up a little bit about the motivations for energy management systems. And without further ado, I'm just going to hand over to the expert team at Spirax-Sarco. And we will be hearing from Dave Forte and Ray McEwen in the first instance. Can I just remind you all to really make use of the chat box and drop any questions that you have while Ray and Dave are talking into the chat box, and we will cover those at the end of the presentation. Dave, Ray, over to you.
Okay, Dave, you should have the screen there. Dave?
Unmute. Okay. Okay. Apologies, I was having some troubles to unmute. Thank you, Eloise, saving me there. Well, thank you everyone for joining us, and thank you Carbon Trust for their introduction and the background to your program. It's very exciting, and I hope those of you that are listening do find today of interest, and I hope we can share some insight with you over the next hour or so on how we can maybe help optimize your steam systems, or how you can improve your carbon footprints with your operations. I don't want to spend too long. I just want to give you perhaps a brief overview of Spirax-Sarco, so you have an understanding of where we're coming from. My name is Dave Forte. I'm the Global Strategic Account Manager for Spirax-Sarco. I'm actually based in the UK, but up to a couple of years ago, I spent 7 years living and working in Southeast Asia. I was based in Singapore. Latterly, I was running our operations in Singapore and what we termed our developing markets of Myanmar, Laos, and Cambodia. So I have some very happy memories of working and living over there, especially my team in Myanmar, who one or two may be online today. Just to give you a brief background, Spirax-Sarco, we are a UK-based organisation. We have, I guess, 3 sorts of divisions. We have our Watson-Marlow brand division, that is a specialised pumping company, and then we have what we term our thermal energy management brands or companies. One part of that is our Chromalox division, which focuses on electrical process heating, temperature management using based around electricity, electrical sources, and where we are coming from, our Steam Specialities division, which hosts our 3 brands of heater control valves, Spirax-Sarco and Gestra, who you may be familiar with. Thanks, Ray. Oh, is that the next slide? Okay, keep step with this, please. Okay, so how we support you, our customers, with our decarbonisation journey, I guess there's three elements. There's obviously eliminate or reduce the actual use of steam on your sites. Sparks Arc over a number of years have been investing quite heavily in research and development and developing technologies that will allow the production of steam or the storage of steam in some extent, should we say, minimizing the use of burning carbon fuels or bio waste or whatever you may have. So we are, as a company, actively trying to support industry in terms of trying to decarbonize, but at the same time retain the use of steam, because I think many of you users of steam know what an efficient medium it is for using energy across your plants. The other option, obviously, if you can't eliminate burning your fuels, you want to optimize your steam system. So we support many customers, we support many of industry in terms of trying to optimize how their steam is used, whether that's through best practice. Some of that we'll share today with Ray. Installation of heat recovery solutions, audits we've already talked about this morning. So there's a lot of activity that we can support around trying to optimize your steam system. And then I think already mentioned, you can put a lot of effort into optimizing your steam systems. You can look at the low-hanging fruit, but after time that low-hanging fruit can grow back. So you also want to think about how you manage your steam system, whether that's through service support. We have things such as steam trap management, and that's now developing into the digital world as well. So there's many ways in which you can also look at how you manage your steam system. Thanks, Ray. So just to give you a little overview of where we are in Southeast Asia, we have operations across the region. Our headquarter is based in Singapore, but we do have our own service, engineers, sales support based across Southeast Asia, from Jakarta right up to Yangon. So we do have quite a broad coverage in the region. We have some central live steam labs based in some of our larger operations, such as Singapore, where if you can join us in our laboratories and you get some hands-on training of steam in a safe, controlled environment. So just as an overview, Ray can just step through this one. This is just where Spirix can provide some support, whether it's with your steam system, what we can support with steam trapping, controls, the automation of your steam system. Again, I mentioned training. We do a lot of training, and I'll mention in a moment how you can maybe access more of that. We do provide a lot of condensate management solutions, and it is a very important part of trying to recover your energy, because it still has a lot of sensible heat left in that nice hot water, that condensate. So being able to manage and recover as much of your condensate as possible is very good practice. And we get involved with a lot of companies who are looking to increase the percentage of their condensate recovery. And I'm sure Ray will explain a little bit more in detail around that in this afternoon's even session. We also provide package solutions, whether they're heat recovery skids, if we're trying to pinch some energy. We also provide things like clean steam generators that, again, can help decentralize maybe some of your steam systems and allow just some focused supply of regulated steam into parts of your production area. We also provide a lot of metering. Again, we're working with a lot of companies who are going down this journey of sustainability, of decarbonisation. And one of the factors is implementing a metering strategy, because once you know what you are using in terms of your steam or how much condensate you're returning, you can then understand what actions you then need to take to try and help perform and optimize your steam system, whilst also understanding where your steam is going and if there's any areas that maybe you can save or minimize using your steam, or even if you have problems, if your condensate return suddenly drops off, you can try and understand and fault find where that condensate is disappearing to. And obviously that's all backed by services. And as I mentioned about our Southeast Asia coverage, we have service support in all those locations. So if there are areas that you want some support or investigation, again, Spirix Arco can certainly provide that locally to you. Thanks, Ron. And then just to finish quickly, Again, Ray is going to go through quite a lot of content this morning in terms of how you best practice in terms of your steam systems. Spark Sarco, we believe in sharing that knowledge and helping industry improve the condition of their steam systems. So you can access a lot of our information, training, knowledge on our websites. There's plenty of white papers. We provide some webinars. Again, they're all accessible on our websites, and even some best practice guides. So please feel free to access any of that. If you do want further information or some guidance to where to find certain topics, please feel free to either connect with us during this webinar, this workshop, or feel free to connect directly with your local Spark Sarco office. And with that, I will hand over to Ray, who will actually get into the real content of this morning's workshop, and I'll leave it with you, Ray. Thank you.
Thank you, Dave, and good afternoon, everyone. So my name is Ray McKeown. I'm based in Cork, Ireland. And for years, I was a global resource and helping our customers through their sustainability journey. So I had opportunity to visit Asia numerous times, but as a visitor and a guest, doing a block of work, moving on. What we're going to do this morning, or this afternoon, sorry, is go through two sessions. First one starting with steam fundamentals. And the reason why we're going to start with fundamentals, because when it comes to energy efficiency, what we need to do is to understand why a system is efficient and the factors that can contribute to a poor system. And from our own experience in supporting our customers through their sustainability journey, what we've identified is that the fundamentals of a steam system are very important for achieving efficiency. So when you look at your own system, what you need to do is to understand where you are, and from that, what is contributing to an efficient system or what can make the system inefficient. From our experience, what we have found is that a biggest problem is the actual design of the system. We find that some engineers don't really understand what a steam system is and design it similar to a water system. And we're finding that a lot of the problems with a steam system is the actual design itself. We're also seeing that the cost for lean operations, reducing an operation cost, that some companies are put under pressure to try and minimize costs where possible. And we're finding then that some maintenance procedures are lacking, not because of intent, but because of budget constraints. And again, what we're seeing is that minimum maintenance or lack of certain maintenance can have an impact. It could mean that the system operates in achieving the production requirements, but might not be the most optimum or energy efficient system. We also see aging assets, and you could say, what does this mean? But you're finding that for some equipment, they might have been designed for a certain efficiency, which would have been acceptable maybe 20 years ago, but now with the drive for modern efficiencies could be improved upon. And even simple things like retrofits. So if a piece of equipment fails, do you put in like for like, or do you put in best in class? And what another key area we're finding is that controls and automation. And this is right across the board from established markets where support from Central Europe to even Africa. It doesn't make a difference of the geographic location, because just because you got the best in class system does not mean you got the best in class control. And what we're finding is that often the controls are lacking or a misunderstanding of control. And then we need to look to see how we can improve efficiency by getting greater control. So when we look at a steam system, we need to understand what contributes to an efficient system. So we'll be talking about boiler efficiency, how we can achieve efficiencies, and as was introduced, there's certain parts of boiler operations which can achieve very attractive savings. We also need to look at the hot well system or your boiler feed water system, and most importantly, its functionality. including the quality of feed water, the type of feed water, and what it means for the efficiency of the boiler. It's also important that we look at the steam distribution system. Why? The purpose of the boiler is to generate high quality steam and export it to end users. However, the quality of steam of end users is not that which is generated by the boiler, and steam, by its very nature, will want to give up its energy to its surrounding, in doing so condensing. And as we know, water is an excellent insulator. So if you allow a system to basically condense steam, you can reduce the heat transfer efficiency of end using plant. We will then look at the heat transfer efficiencies of those users, what can be done to optimize them. And then importantly is that to look at your condensate recovery, or what we call your recoverable condensates, because within the food and beverage sector, some of the steam can be used directly within the process itself. However, what's important to do, which was mentioned in the introduction, is that conducting and maintaining an efficient steam system is not a once-off process. It's a continuous process. And you need to continually re-look at the systems to see where current and future savings can be achieved. So when we go talk about steam, what are we talking about? Steam is very versatile and easily adaptable to changes. It's the technical term for water vapor. It's also the gaseous phase of water. However, when it comes to efficiency in steam systems, it must be understood that steam is a biphase system where you have biphase states of water and vapor. So within the steam system, you can have entrained water droplets. What that means is that as steam starts condensing, it creates water. And even in a steam distribution system, you could have small droplets of water in the steam, and the volume of water is known as the steam dryness. So you're looking to get to unity or one, which is pure vapor. As you come back down towards fully condensing water, your dryness drops off, and where effectively you want high quality dry steam. Why steam is used within the food and beverage sector? Because it's got a high energy content relative to its volume. So in other words, you can get a high energy input to your end users with such a small volume when compared to water, for example. So on a kg per kg basis, steam holds about 20 times more water, 20 times more energy than water. However, it's fair to be said that steam is often fraught with issues, is considered an inefficient system, a troublesome system. However, reasons for that from our experiences, again, through design, lack of effective maintenance, and again, misunderstanding what contributes to an effective steam system. So when we start talking about steam, we need to consider the three main properties. So we have the enthalpy of steam, which is the energy. It's both sensible and latent. Sensible is where you heat water or gas, basically by increasing its temperature without a phase change. Latent energy, which is the highest part of the energy content of steam, is where you're changing its phase or state. So, i.e., from a vapor back to a water. And that's what steam wants to do. It wants to give up its high energy content by condensing. We also have steam at different pressures. We'll be talking about why you could select the pressure for your application. And importantly, we talk about specific volume, because when it comes to steam systems, the higher the pressure, the lower the volume, which means you can get large volumes of steam for smaller sized pipes, which helps with the installation costs. So within your boiler is designed from what's known as a from-and-at rating. And what that means is that it's designed to generate so many tons of steam basically within an hour. So if your boiler is designed for, say, 10,000 kgs an hour or 10 ton, it's designed to generate 10 ton of steam at atmospheric conditions. However, let's consider the process in the boiler. So if you were to take, say, a kg of water, and you were to add heat to it, this is the sensible part of it. What this means is that you have to take water, for example, from 0 degrees to 100 degrees by adding heat. In doing so, you will not change the phase or state of water, but you will add energy up to a point at which it will then start transitioning towards its latent phase. However, when we start looking at the energy content of it, and the specific heat capacity of water is 4.186 or 4.19 kilojoules per kg. So we need to add 419 kilojoules of energy to raise water from 0 degrees to 100 degrees. At this point, it is purely a sensible process. We're just effectively heating water towards boiling temperature at atmospheric pressure. Then to create steam, we need to add additional latent energy to a point where we get it up to high quality dry steam. At atmospheric conditions, we need to add additional 2,257 kilojoules to produce 1 kg of steam at 100 degrees. The difference in the latent phase is that you change the phase or state of the water without a change in temperature. And this is important because it's a constant temperature energy switching or energy additional process. Now, when we start looking at the enthalpy table, you can see is that we start our process where we start adding energy, and this is known as the liquid enthalpy, where we start from point A to point B in raising the temperature of the water in adding energy basically to a point of 419 kilojoules. We then start adding additional energy, and as we start moving, sliding across this dryness fraction scale, the more energy we add, we'll come to a point where we create what's called dry saturated steam with a unity dryness fraction or fraction of 1. If we generate steam with a reduced dryness fraction, say for example 0.9, what that means is that we have only 0.9 times the available enthalpy of evaporation because we have 10% per volume is still water. So it's important that when we're considering steam to end users, we consider the dryness fraction, because this has a significant and often unrecognized consequences for steam quality and steam efficiency and reliability of plant. If we add additional energy from point C to D, we go through the superheated phase, where basically we start increasing the temperature of the steam, and you would use superheated steam for the likes of steam turbines or certain critical plant. However, for most food and beverage industries, we only operate within the normal dry saturated steam region, because within the process, what we want to do is for steam to give up its energy at a constant temperature. So when we start looking at our total enthalpy, you can see is that the energy that's in the condensate, or enthalpy of water, as represented in the blue zone here, is about 420 kilojoules. Our enthalpy of evaporation, for basically 0 bar steam, again, 2,257 kilojoules. But our total available energy per kg of steam at atmospheric pressure is 2,676. Within our processes, what we want to do is basically condense the steam back down to its enthalpy value. And in certain applications, we then subcool the condensate to get this residual energy out of the enthalpy of water. This makes a difference when it comes to high pressure condensates, because at the moment we're only talking about steam at atmospheric pressure. Now, to understand what this means is that there is tables have been created which shows you that for different pressures, what enthalpy you can get from steam. So within your boiler, which is designed for a Frominat of say 100 degrees, you can see that according to the steam tables, the different enthalpies that you can get from the steam, from enthalpy of water, enthalpy of evaporation, and the total enthalpy of steam. However, you do not operate your boiler at 0 degrees, and you will operate your boiler at a pressure relative to your process. But what you can see is that if you slide down this basically scale, you can pick a point. In this example, I'm just showing 1 bar, just for example. What you can see is that in this scenario, you have to increase the water temperature to 120 degrees before it will start evaporating into steam. So in other words, there's a higher energy content required just to bring water to that boiling state. You can also see is that the energy required for evaporation has reduced because there's more enthalpy in the water to flash and generating steam. And you can see that although the total enthalpy of steam has increased, it's not a significant step change. So in other words, when you start looking at the total enthalpy of steam, it doesn't change much between one pressure to another. The biggest differences are the temperature that's required to boil water and the enthalpy of water that's required to bring it to boiling. However, more specifically, is that when we start looking at the specific volume, you can see is that as we start increasing the temperature, the volume reduces. And this has a big significant impact on the ability of steam distribution systems to basically carry steam to end users. And we will go in a bit more detail on this in a minute. So again, when we're just looking at on a simple chart, as you increase pressure, the total enthalpy of liquid water increases, the enthalpy of evaporation reduces. But you can see is that although there's a subtle increase in the total enthalpy of steam, it basically near stays steady. When we start again looking at pressure, so within your boiler, you will generate steam at the required pressure. In doing so, if we look at different pressures which are used in industry, so we'll see 10 bar, 25 bar, for example. So you can see in this case, we have to increase our water temperature to 184 degrees before we start evaporating. You can also see the different enthalpies of evaporation that's required to bring it up to dry saturated steam and the total available steam. Now, when we start talking about specific volume, reason why it's important to understand why we generate steam at certain pressures and why we distribute at certain pressures is that let's take an example of we need a process that requires 5,000 kgs an hour. So if we are to generate steam at 4 bar, you can see that according to sizing protocols, to ensure we don't have a velocity greater than 25 meters per second, you would need a DN200 pipe at 4 bar. Reason why you need this size pipe is that you need to ensure that you can accommodate the 5,000 kgs an hour within standard pipe size. If you go to the smaller DN of 150, you won't be able to accommodate the 5,000 kgs an hour. In this scenario, you might get a total of 7,500 kgs an hour. But the key point is that you need a DN 200. Now, if we look at 10 bar, for example, to get the same 5,000 kgs an hour, you actually need a DN 125 size pipe. Although the total capacity will reduce to 6,200 kgs an hour, we're looking at a process that only needs 5,000. Why we advocate to generate and distribute at high pressure is because installation cost for piping is quite significant when you consider not just pipes and ancillaries. So it's important that you generate and distribute at the highest pressure possible, such that you can get the lowest installation costs, but done so in such a way that you can ensure that you can get ample supply of steam without creating steam starvation. And you can overcome issues such as what is normal problems with systems in that process can't achieve temperature or struggling when another process comes online. So this is important to understand that the ability to transport steam is determined on its pressure at a certain pipe dimension. So, however, what we need to consider is that Although we advocate to generate at the highest possible pressure and distribute at the highest and acceptable pressure, we need to consider that end users operate to certain temperatures. Within your very process, you're controlling most likely to a temperature. However, if we take our 10 bar boiler and we look at this profile, what we can see is that at 10 bar, according to the steam tables, you're about 185 degrees, a temperature which is often too hot for certain processes and may cause product spoilage. What you should be looking to do is generate and distribute at the highest possible pressure. Then at point of use, you would then look to see, like in this example here, we want the process at 120 degrees. So when we start looking at the steam tables 120 degrees, reality we see we only need steam at 1 bar. Now, that's assuming optimum heat transfer efficiency. In this kind of scenario, you would say that you should control to 2 bar to give you controllability such that you can achieve the 120 degrees. So what you should be looking to do is to have point of use pressure reduction such that you get the temperature and pressure that's required by the end user. Another reason why you reduce pressure is that you get greater controllability by temperature and pressure regulating valves for end users when you have a lower differential pressure across the system. So you get better control. The choice of the pressure reduction station will be determined on the criticality of the pressure. So you can go from self-acting controls to basically fully automated controls with digital controllers. Now, they're kind of introducing the basic concepts of steam generation, the enthalpy of steam. So again, to understand when it's talking about steam, that again, to recognize that steam is a biphase system, has water, has vapor, and to understand the impact one has over the other, because as we start talk now about the fundamentals of distribution, it becomes evident why it's important that we generate highest quality steam and distribute highest quality steam as possible. Now, let's start talking with the boiler. So within the boiler, what we are trying to do is to generate high quality steam. However, its ability to generate pure, dry, 100% dryness fraction steam is determined on its load factor or duty. So in other words, how it operates in response to process demands. If the process demand is very erratic, there's a tendency that you would basically carry over water into the steam system. So it's important that you arrest this flow of water before it gets into your steam system and creates problems. So from the connection or crown valve from your boiler, you should put in a steam separator. What the separator does is that it removes the water that's generated from the boiler and carried over from the boilers within the steam before it gets out in the steam system. We always put in steam meters, but the problem is that we're not conditioning the steam in advance of the meter. And from our experience have found that steam meter data can sometimes be unreliable because the quality of steam that's supplied to it might not be the best. And steam can be corrosive if there's a lot of water entrained in it. So you're doing two functions. You're ensuring that you have very high quality steam to your distribution system, and you're protecting down system plant. You should then look at pressure reduction from the boiler to the distribution system. Why? The boiler is designed to generate steam at a certain pressure and should operate within its design parameters. However, you may not want the same design pressure within your distribution system, because the higher the distribution pressure, the higher the distribution losses. So you should then immediately step down your boiler pressure to your distribution pressure, such that you can minimize the distribution losses while still operating the boiler at its design condition. You should also be looking at best practice, because from our experience, what we have found is that a lot of sites are struggling to do maintenance because they can't take down plant with a level of safety to ensure that maintenance craft can work on additional plant without cause for pressurization or steam leakage. So it's best practice to put in what we call double block and bleed, using a high quality valve with this kind of configuration here. And with this configuration, the whole idea is that you have dual isolation, one isolating the boiler, two isolating the distribution header, and the bleed valve, which you would fully open. So if there was any leakage from either system, it would leak to a safe discharge point. In other words, you could totally depressurize a boiler while still maintaining a steam distribution system at pressure from additional boilers. Now, when we said we want to generate high quality steam, remember, steam will want to release its energy as soon as it comes in contact with a system or process, or even a distribution system at a lower temperature. So we call this distribution losses. Within your steam system design, you need to basically counteract this process by ensuring that you have effective condensate removal throughout your distribution system. Because, again, the steam will want to release its energy. It's an inherent function or feature of steam. And a lot of the problems we're coming across is that there's ineffective consideration towards, condensate removal, mains drainage, and an effective steam distribution system. So we're going to go through a few different pointers of what we call worst in class and best in class. And this is based on system findings. So when you start looking at trapping, the function of distribution trapping is to remove these condensates which are generated by the distribution process itself. However, in this scenario, what you will find is that, again, please remember, you have a flow of steam at velocity through a pipe. So we're seeing plenty of cases where you have a small tapping like this into a trap. Although it will remove condensate, it won't remove all the condensate because condensate will be pushed past the trapping point or tapping purely because of the velocity of steam. This is the best in class, in where you would install what we call a full-size dirt pocket, where the condensate under gravity would fall into this dirt pocket and being removed by the trap, such that you don't carry on water or condensates to the end user or the next part of the distribution system. When we start looking at pipe reducers, because again, we distribute a certain pipe size, and what we do is we reduce the pipe dimensions as we move out towards the index parts of the distribution system. Often we see these ineffective concentric reducers, and what you would see is that you create like a sump of condensate sitting on the lower part of the larger pipe. What will happen is that under certain velocities, you will end up dragging this water or condensate like a wave into the distribution system, creating water hammer problems. And we will discuss water hammer in more detail in a minute. So when it comes to reducers, it's important that you have an eccentric reducer such that the condensate can move freely along the base of the steam distribution pipe. Where you have the effective dirt pocket can be removed more effectively. We also should look at the pipe connections. And often we come across a scenario like this, where you would take a tapping to an end user, and basically you would drop from a vertical line down to the end user. In this scenario, however, the condensates in the distribution system will fall down into the end user, and you will find you could have a lot of water hammer problems, poor heat transfer efficiency, and very ineffective control. It's more beneficial that you take a tapping from the top of the distribution pipe. You should also look at an isolation valve as close to the tapping point as possible. And in doing so, you only take dry steam to your end user, eliminating problems with water hammer and poor heat transfer efficiency for that end user. So let's explain a bit more about water hammer, because again, this is a common problem with steam distribution system. So if you take your steam distribution header, again, please understand that it's not just a steam vapor, because a steam system by design will lose heat unless you control against it. And the heat loss is determined how effective the insulation is or the design of the system. However, what you will find is that in your steam system, you have a biphase system, which is a mixture of steam and condensate. However, what you will find is that the end user will determine the velocity of steam. So the water velocity, or the motion of condensate at the base of the water, does not travel at the same velocity of that of steam. And sometimes the steam velocity can be 10 times greater than that, than the condensate flowing through the pipe. However, you will also find is that your process systems might be on, off, batch orientated, or you could have different changes or stages and recipes, which will determine additional steam demand. In doing so, what you will do is that, in effect, the increase in velocity would basically pick up this condensate, in effect creating like we call a slug of water. So this slug of water creates what could be described as a piston, or a hydronic piston, picking up velocity as it does so, because in creating a water seal in the condensate pipe or steam pipe, you reduce the pressure at the downstream side of it, and with the pressure of the steam system, you increase the velocity even faster and further again. What happens though is that once this water hits basically a system restriction, like a pipe bend or a valve, for example, it gives up its energy as kinetic energy, and often creating a loud banging noise. And it could be visible in steam systems by pipes vibrating, shaking, rattling, but very audible loud noise, which is similar to like hitting the pipe with a hammer. However, if you then look at ineffective condensate management, condensate drainage, the consequences are, we have come across case examples where you would have valves being destroyed purely because the continuous water hammer damage has damaged the structural integrity of the valve. And again, you see cases where valves break and shear in releasing steam, which can basically be a health and safety hazard, irrespective of the energy. And again, multiple case examples where valves and system equipment have been destroyed because of this water hammer. However, this is addressable because it's about steam system fundamentals. So when we start looking at our steam distribution system, what we look at is that there is best in practice guidelines on condensate removal to remove this water hammer issue. So you should have on a distribution system at least 30 to 50 meter intervals a steam trap station. And our engineers within a region would always be advocating, oh, you need effective trapping. There's reasons for this, because if you don't remove the condensate effectively, you create water hammer issues. If you water hammer issues, you have very poor heat transfer, and you end up damaging end plant or distribution systems, like which was shown in the previous slide. When we start looking at the dirt pocket, up to a certain pipe size, so up to a DN100 or 100 millimeter pipe, your dirt pocket should be the same diameter as a distribution pipe. When you go to different pipe sizes, so from a DN125 to 200, your dirt pocket should be at least 100 millimeter. And for a 250 millimeter pipe and above, it should be half the size of your distribution pipe. So having a small DN15 or DN20 tapping means you're not really effectively removing condensate from a distribution system, and you're only having a marginal effect. So when we start looking at steam dryness, so what's also important is that we should look at separation, because even within the steam system, that as steam moves through the distribution system, it picks up these water droplets because of the velocity of steam and the piping. So what you will have is that droplets of water are in your steam system. And again, water is an effective insulator. So as these droplets move forward, they create erosion. They basically have an impact on plant reliability and reduce the heat transfer efficiency. It is therefore important that to recognize that trapping alone, even though it's the best-in-class trap installation, will not remove all the water. It'll remove the water, the sump of the pipe, but not that entrained in the steam itself. Therefore, we should look at separation, because the function of a separator is to basically remove these water droplets. What it does is that as wet steam moves through your distribution system, what you're doing through the separator is that you're reducing the velocity of steam as it transitions through the separator. In doing so, the water droplets under its own gravity will fall out of suspension, collect at the base of the separator, and basically gets removed effectively through proper trappage. What you have then is high quality dry steam to your user, whereas that having higher enthalpy of steam means that you have higher energy available to your end user. So, for example, on a kilowatt basis, if you can supply steam at a unity dryness fraction instead of, say, 0.9, you will use nearly 10 to 15% less steam on a kilowatt basis. And it's important to understand that if you can have higher quality steam, then your boiler has to operate, to do lesser duty, because it's only operating using steam at the highest properties. Now, what I want to demonstrate here is, please understand, this is a laboratory condition. It was done so to demonstrate the effect of wet steam. Please do not copy this within your process, because this was done through a controlled condition to basically demonstrate what wet steam is. So what we have here is a test lab in one of our offices, where we're effectively showing that what a separator is, the impact on the operation separator. So this is your separator here. And you can see in this condition that we're controlling the discharge of steam, but we are not allowing the condensates to be removed effectively by the separator. It should be understood is that wet steam is very visible to the naked eye. And you can see here is that as he puts test pieces of paper in, you can see how saturated the paper has become, because effectively the distribution steam contains a lot of water. Now, what he's looking to do here is that he's now bringing the separator online. And what he's doing is that the separator then, as you can see here, is removing those water droplets from the steam system, such that you get high quality steam to your user. He's now going to test his steam to his end user. And you can see is that in this condition, that the test paper is quite dry. So in other words, we are supplying high quality steam to the end user. Again, it should be understood that wet steam is an insulator. It reduces heat transfer efficiency, increases the likelihood of water hammer, and reduces plant reliability. So through a separator, you have high quality dry steam to end user. This process can use the full enthalpy of evaporation of steam. So in other words, you can reduce your demand of steam system when you're using higher, better quality steam. Again, please understood, these are test conditions, and the test was conducted to demonstrate the purpose of the separator. So let's consider some additional best practices. So one, we spoke about the trapping, but it's also important to understand how you interconnect to your condensate system. Again, we're seeing case examples where the traps would basically be installed and interconnecting to the base of the condensate system. Like the steam system, any condensates that are in this distribution header will basically backfall under gravity into the system and making it difficult for this trap to operate effectively. What you should do is that from your trap outlet through your riser, you interconnect to the top of the pipe. So in other words, that the condensates in this pipe should fall under gravity to its receiver. And in doing so, you're discharging where you're basically not discharging into what is effectively a flooded header. Where you have certain mains distribution traps, so for example, a thermal dynamic trap, which is a blast function, you should have a diffuser installed where it interconnects to the steam distribution system. The reason for the diffuser is to basically reduce the kinetic shock to the condensate system when you're discharging condensates and steam at high velocity. Now, what we also need to consider is that for most of your applications, you are basically out of a heat exchanger, for example, into a trap, up through an elevated header, like in this scenario here, back into your condensate line. However, what we need to understand is why systems operate and what can cause stall. So stall is the term given when a heat exchanger is struggling to impact heat such that you cannot achieve the temperature set point, or under certain duties, it's failing to perform as it should. In this case example here, let's consider that we're rising 12 meters back up through this header into our main header. However, what we should understand is that each 1 meter of water column height creates 0.1 bar back pressure on the trap outlet. So in this scenario here, we have that on our pressure gauge, if there is no operation, you'll find that this pressure gauge would basically indicate 1.2 bar. If we go to the top of our steam condensate header, our pressure gauge will show us 0 bar, because if this pipe interconnects to atmospheric pressure condensate curve unit and drops under gravity, then we should be a 0 pressure system. Now, what's important to understand is that where you have a water column height, if this back pressure is greater than the pressure that's within the heat exchanger, the system will stall. What you need to understand is, according to the steam tables, is that pressure is proportional to temperature. And when you're controlling to a temperature, especially anything less than 100 degrees, it is very common to have atmospheric or sub-atmospheric pressures within the heat exchanger here, even if you have steam pressure available to the control valve. So where the pressure is less than here, the trap cannot remove the condensate effectively, and you'll experience temperature swings, poor control, or lack of controllability. In this scenario, we advocate you put in what's called the pump trap. The pump trap effectively uses steam, where it basically, if the system is in stall mode, then the pump trap goes into pumping mode and uses steam from an independent supply to basically pump the condensate back up to the user. So it's important to understand that steam traps only work under differential pressure. And if the pressure to the application is less than the back pressure being exerted in the trap, it won't work. And that's irrespective of manufacturer. So again, assess the application. And if you have scenarios where you have the problems we just mentioned, then you should be looking at the pump trap as a means of overcoming stall. It's also worth noting is that on part of these risers is that if you have a high pressure application, then within this condensate pipe here, you would have some of these condensates turning into steam, because as it reduces in pressure, the thermodynamics of steam means that it will try to basically create steam within itself. In doing so, what we should try to do is keep these rising lines as short as possible, that you shouldn't be, say, for example, operating at a ground floor process and elevating up the full height of the building. You should be trying to basically create a condensate system where you're interconnecting to, say, a ground level condensate curve unit. And you should have distribution headers at the one height of, say, the per floor. So for example, you should try and keep these headers at this as close as a ceiling elevation for the floor you're working on. And you should have multiple headers all feeding into a common riser back into the condensate recovery system. Not a single riser up to the highest point in the building and then dropping down to the condensate vessel at the lowest point of the building. We mentioned about the flash steam. So let's consider a high pressure application. So say, for example, we have a process that's operating to, for example, 160 degrees. So what you're going to do is that you will have high pressure condensates at this point here before the steam trap. Now let's consider after the steam trap, which is interconnected into a low pressure or zero pressure condensate header. So in this case example, we're going to consider what we call a flash vessel. However, in this flash vessel, what you have is that once you depressurize this high pressure condensate, the energy in the residual condensate will want to try and give up its excess capacity above that, which you can hold at 0 bar. And if you can remember, is that we talked about the enthalpies of water in our steam fundamentals, and the higher the pressure, the higher the enthalpy of water. Conversely, what it means is that if you're to reduce pressure, then that condensate cannot hold on to that energy due to the thermodynamic laws and will release this energy as what we call flash steam. So in this scenario, what you'll find is that you will generate flash steam and you'll generate low pressure condensate. If this was your condensate recovery unit, what you're seeing is that on the vent from a condensate recovery unit, you're seeing a lot of flash steam. And this is unavoidable if you're using high temperature processes. Now, let's consider that if we're case example that this was 7 bar. So according to the steam tables, water or condensate at 7 bar has enthalpy of about 721 kilojoules. However, please remember that condensate at 0 bar can only hold 419 kilojoules. So steam condensates will want to release the difference between the 721 minus the 419. And when we look at the enthalpy evaporation, it will generate about 13% of the condensate will convert to flash steam. Again, unavoidable and often seen as flash steam coming from condensate recovery systems, because in reality, in most cases, you're going back to a condensate recovery unit. For your own application, we mentioned about the tools and literature we have freely available. So you can see there's sizing charts that you can very quickly see that the pressure of your application, the pressure of your condensate, you can see exactly how much condensate it will theoretically create. And again, in knowing this, you can then see how you can improve the efficiency for those users. And it's important to not forget is that this is unavoidable. So any high pressure application which reduces high pressure condensate to low pressure condensate through a 0 pressure condensate recovery system, you're going to create flash steam, and it is unavoidable. Next, we're going to look at control valve classification. So we talked about the distribution system and getting high quality steam to the end user. Now let's consider simple things like control valve classifications. So when we look at the type of control valves which are commonly installed, although you have 6 classes, the 2 most common ones which are in use are the class 4 valve, which is normally referred as a metal to metal valve, and the class 6 valve. The difference is that as you rise up through the classifications, its design leakage rate is a function of the class of valve which is installed. So you can see that a brand new class 4 valve is designed to leak 0.1% of its max load allowance. So in other words, is that if you have a valve designed for 20,000 kgs an hour, it will leak by design up to 200 kgs an hour of steam. So in other words, you can get high leakage rates by design. From our own lab analysis, where we have basically taken different types of valves and stressed them to what is normal operating conditions, what we have found is that although it might be a class 4 on installation, within a very short period of time, 6 months to a year, you're at a class 3. So in other words, you have high leakage rates. It's therefore far more economical to look at the class 6, which is designed to give complete shutoff. Because where you need to consider the different types of valves. Again, what I'm showing here is a little case example of a customer we visited, and you can see here that the steam valve is at 0% output. However, what you can see is that over time, his class 4 valve has effectively, the seat has eroded. And you can see is that we're continuously putting steam into what is an open chamber. In your process though, you need to consider two things. If your process is continuous, where the steam is 24 hours a day, 7 days a week, you could argue the class 4 valve will suffice, because by virtue of the fact is that there's always addition of steam. However, if you have a batch or intermittent process, or where it's integrated, like in this case example for pasteurization, any leakage on the steam system translates to additional cooling when in the cooling phase. So it's important to understand that you should be looking what we call life cycle costs. And what this means is that you don't look at the cheapest valve, you put in a valve designed for the application. So if it's on, off, or intermittent, you should have a class 6 type valve. If it's a continuous operation, a class 4 will do, because you will always be controlling a steam supply. So finally, we're just going to talk about steam trapping. So when we mentioned about the continuous assessment, what we need to understand is that a steam system requires continuous improvement. You should assess your steam trap population at least once per year, because if we take international best practice, your failure rate should be anywhere around 5 to 10%. So what this means is that conducting a once-off trap survey is good for the calendar year which you have done it. But again, analysis through international best practice has identified that there's about an annual 10% year-on-year failure rate. So, for example, if you were to take a single DN15 trap on a 6-bar system, where you have a trap population of 100 to 200 kgs, a trap population of 100 to 200 traps, you could be leaking anywhere from 180 to 260 kgs an hour steam, even conforming to best practice. So what that means is that this is where you should be. Reality, best in class is 5%. From our experience, we're seeing failure rates as high as 30% for some industries. So you can see that your leakage rate can be quite significant. So what you should be doing is to catalog your trap population, identify the traps in your system. Also, there's no one best fit trap. So, Swarwick Sarco, like any other trap manufacturer, will recommend a certain trap for a certain application. And although some traps are more expensive than others, it's designed for a specific purpose. So you need to install the trap that's designed to do what it's meant for. So in other words, that you should be not looking at initial cost, but life cycle costs and reducing system maintenance costs. And unfortunately, and what we're finding is that for those sites that undertake trap surveys, they're good for doing the survey, but acting on the findings due to operational constraints can be an issue. So what we are trying to do is look at easing those kind of procedures through what we call a double block and bleed type trap, where basically you can do the isolation and remove the failed trap quite effectively. So with that, we shall end our session 1, which will be good now. Take you back to Elise for the questions and answers session.
Thank you very much, Ray. So I just want to say thank you for that first session. It's really good to get us started on the presentations for today. So we are now moving into our Q&A session, and our first Q&A session. And I just want to say there are some really great questions coming through already. So that's fantastic. Please do keep them coming through, and I will do my very best to moderate and show the best of the questions that we can today. So what I will do first of all is just go through a few of the questions that have just come up on the chat bar and direct them to the Spirex Sarco team. So Ray, while you've been speaking, all the questions have been really flooding in to the chat box, which is really great. So starting with some of the steam system fundamentals, first question is, at which pressure can we ensure that the steam to end users is dry and saturated?
There is no simple one pressure that fits all. What you should be doing is, and we'll discuss this more, is that if the steam boiler is designed to generate steam at 10 bar, then you should generate steam at 10 bar, and as recommended, reduce the pressure to a distribution pressure. Often what we're finding is that industry is being misled in reducing boiler pressure, say for example from a 10 bar design to 6 bar, because you need 6 bar by the end user, or distribution pressure. But you can't take a boiler that's designed to operate in a certain condition and have it operate in a different condition. And what you're finding is that, you know, it inherently creates wet steam, which then creates the problems of heat transfer efficiency and the water hammer issues and poor distribution systems. So there is no one pressure. I would suggest you operate your boiler to design pressure, and then you take note of the, you know, distribution considerations like separation, effective drainage, etc.
Great, thanks, Ray. Where is the best place to install a vent from a receiver? Can a long vent line be a problem?
Yes. If you take any pipe that has restrictions to flow, it creates back pressure. So what we have found for certain industries is that due to whatever reason in the production area, you have very extended vent pipe going to, say, a roof level. And all condensate recovery receivers should have what we call an overflow siphon. And that's designed to basically stop the condensate header from flooding should the condensate pumps fail. And in that case, what you would find is that in the extended vent line creates a back pressure in the condensate receiver. And effectively, if you pressurize the receiver, you blow through the overflow siphon. And if it's in a production space, you could find steam venting into the production area, which is unwanted and could cause issue with plant reliability for control cabinets. So shortest run possible is the best answer.
Great. Now moving on to steam separators. Does the steam separator need to have a frequent service? And where is the best place to install a separator? Do we need one at the boiler and the steam user point?
So there's 3 best locations. So we mentioned the boiler. So again, it's important to remove the wet steam before it gets to the distribution system. If your steam system is basically an external distribution system, you should do so on entry into the building. Because where you have an external distribution system, your steam header is open to the environment. And, you know, from the geographics of, you know, rainy seasons in, you know, Asia, you know, a lot of rain, wind, etc., can have an impact on the heat loss in the external distribution system. So important to put it on where the header enters the building. Finally, for critical end process users, so where it's important to have, you know, good control to the, say, a certain heating application, you should also install it there. So 3 key locations.
Okay. A couple here on methods for checking steam traps. So how many methods are there, and what in your view is the correct way to check steam trap functionality on site?
Okay. The 2 I suppose common methods is a thermal imaging camera and ultrasonic. From our own experience, we would recommend that the ultrasonic, so the sound gun, because what a trap is meant to do is to depressurize condensate. So we mentioned earlier that, you know, you would have high pressure condensate on one side of the trap and lower pressure condensates on the downstream side of the trap. So your thermal imaging gun is going to show that there's effectively differential temperature across the trap. A failed open trap is always going to have a differential pressure, because even though it's failed open, you're going to see lower pressure on the downstream side of the trap. We would therefore recommend that you should use the ultrasonic method, which is basically you listen to the trap, and through knowing the working parameters of the trap, determine whether it's working effectively or not. This is what we do through our steam trap services, because there's a bit of expertise and knowledge in knowing how a trap works and the function of a trap, and determining whether a trap is failed or not. And often we've seen cases where customers have replaced quite good working traps for wrong reasons, and have left failed open traps installed, not understanding that they're actually broken. So would recommend ultrasonic steam trap tester.
A question here about flash steam. So how can you minimize flash steam after a steam trap? Okay.
Again, as per the thermodynamics, if you have condensates greater than 100 degrees, you can't eliminate, it's unavoidable. It's the principles of thermodynamics. Once you depressurize high pressure condensates or high temperature condensates into an atmospheric tank, by the principles of the thermodynamic laws, it will release that energy and you can't avoid it. So unfortunately, it's one of those scenarios that there's nothing that can control against it. However, we'll see in the next session is that we can control how to use this energy more effectively to counteract its I suppose, the generation of this flash steam.
Fab. So I'm taking note of all your questions coming through, and I apologize if I haven't got to yours yet. And any that we don't get to speak through on this live event, we will direct to the Spirex team to follow up afterwards with some advice. I want to make sure that we have a nice bit of time at the end for questions, and we will continue to answer the questions that are coming through. So Ray, I think it'd be best now if we move on to the next session, and maybe some of the questions that have been asked will be answered in your next session around looking at efficiencies in steam systems.
Okay, so thanks very much, Lee. So I'll continue on. So within session 1, we discussed about what contributes towards an efficient steam system when we consider steam fundamentals. The reason why we introduced the fundamentals like flash steam, because where it's unavoidable, you can have a high energy loss. But we're going to demonstrate now how we can counteract that. So let's start off with some simple introduction as to the efficiency of the steam system. So as was introduced during the introduction, is that when you start looking at your steam system, in general, your steam system can be very inefficient. And this leads to how you can achieve such very good or very attractive energy efficiencies. When we consider a study conducted by the International Energy Agency, they have determined that in general, that only about 55% of the fuel energy that goes into a steam system is used effectively by the process itself. So in other words, a very inefficient system. And they have identified, when you consider the energy losses in a system, what actually happens and what contributes towards those losses. Throughout the next few slides, what we're going to do is give you a bit of insight on how to counteract these losses to improve the efficiency of your total steam system. I'd like you just to please just remember this introduction slide, because once we come to the conclusion of this session, we'll revert back to the slide and give you some insight as to how to further optimize your system. However, let's start off with, before you can achieve that, you need to understand your own system. So firstly, the age of your system. Also, you need to consider is that whether you operate like shutdowns, do you have time to basically do effective maintenance on the system? What are your operational hours? Is it 24/7? Or do you have 5-day-a-week production? So in other words, do you have time to do maintenance on your system? Controls and automation. Again, we mentioned that although you may have the best-in-class installed controls, from our experience, that doesn't mean that you have optimum control. And unless you can get effective control in your system, you will have an impact on the quality of steam that you generate and also how you're using steam. is there a process change? Because what you'll find is that your factory over time will change. So if designed 20 years ago, it's probably unlikely that you have the same type of production that you have then now. So is there new production lines? Is there process changes, or has some production lines been made redundant? We talked about maintenance, again, effective maintenance, calibration, because when we talked about control, what we need to do is that where you have any instruments that have an impact on the efficiency of a system, they should be on a calibration regime to ensure that they're accurate and reliable. And what we're also finding is that sometimes technician expertise could be lacking, not through own fault, but again, the drive for lean operations means that sometimes knowledge is lost. Again, performance, what we see is performance over time. You get a drop in efficiency, or the energy performance indicator becomes worse over time because of the impacts that other points we just mentioned. We also spoke about design, and again, time and time again, we find that poor design is a significant contributor to poor efficiency. And lastly, we look at site expansion. How's your site grown over the years? Have you added additional steam systems? But most importantly, the choice of how you interconnect to the existing steam distribution system. Because remember, we spoke about pipe size, pipe dimensions, and steam carrying capacity. People think is that sometimes, oh, let's just interconnect to the steam header here, the steam system will work effectively, without doing the due analysis to see, is it the correct connection point and the impact it may have in the boiler house, for example. Once you start looking at all those different aspects, then you basically find the pointers where you're tipping the scales between efficiency and cost. And reality is, over time, what we're finding is that all these have a different impact on your efficiency, your steam system, and if unchecked, can reduce the efficiency over time. So we're going to give you some basic recommendations. So what you need to do is understand your current system and where you sit on that sustainability or efficiency journey. Dave mentioned earlier about traps and meters, especially meters, because what we're finding is that the need to validate and ensure that you've achieved savings is becoming very key. So measurement and verification is important, but what we're also finding is the accuracy of some metering is quite poor because it's installed meters have become damaged due to the water hammer issues or erosion problems we spoke about. Also, we need to ensure that you're understanding your baseline energy, because there's an expression, it's difficult to save what you don't measure. So in other words, if you've no visibility on how you're using steam, how do you recognize how to improve efficiency? It's also important that you integrate your stakeholders, your system owners, because understanding their processes, although you may come from utilities, you need to speak with your process people to understand what needs to be done to ensure there's uninterrupted process operations. And also, is there any problematic areas which need addressing? It's also important to understand the synergy between steam generation and utilization, because the ability of a boiler to generate steam is determined how you consume steam. And it's also important to recognize that, I've seen, which one of the polls that, there's a high kind of interest in projects and energy opportunities. But what you'll find sometimes the impact of one project may influence another. So in other words, for example, here, that if you improve your feed water quality, you're going to reduce your blowdown demands and the ability to recover energy from blowdown, boiler TDS blowdown, sorry. However, what is also worth noting is that you can learn from each other. So within the next few slides, I'm going to present the findings that was done for one of our international customers. So as a business, Spirax-Sark are heavily engaged with multinational companies in basically being recognized as a knowledge partner in supporting them through their sustainability journey. This information here is based on audits which were done at a global level, where we're going to introduce some of the opportunities which were identified. I've categorized them into kind of key areas so you can get some insight as to what we've identified. It's also worth mentioning is that this is a multinational company, and it gives a broad spectrum from industries from Europe, Americas to Asia. So in other words, it's not just say Asia-centric where there's the problems are Asian problems, or European-centric where the European problems. It gives a good broad oversight. And also it's good to understand is that in Asia, you're no different to Europe or America, the problems are the same. So let's consider the type of opportunity. So we've categorized our opportunities into kind of what we call 8 kind of pillars or standards. So you can see from boiler house optimization, production optimization, waste heat recovery, insulation, condensate recovery, HVAC, steam trap, pinch. Where you can see is that the energy savings per category. And also you can see is like, for example, here for boiler house optimization, in 66 of the sites that we audited, we found that there was cause and need for boiler house optimization. However, let's look in a bit more detail and simplify the findings. So you can see what are core steam engineering fundamentals. So steam trapping, we found is an issue at 25 of the sites we visited. Insulation improvements. So simple things about ineffective insulation, 36 of the sites. Boiler house optimization, separators, drainers, boiler pressure, that kind of thing. So you can see, again, simple things. However, let's look at it in a different perspective. So let's start looking at the opportunities in the Pareto format. So in other words, out of 100% of the energy that's basically can be recovered, let's look at it in simplistic terms. So in other words, when you consider that, without really looking at complex engineering, and it's important to recognize that efficiency in steam system do not have to be complex. So in other words, what we have identified through analyzing this customer data, that over 50% of the identified savings can be easily achieved through core steam fundamentals or addressing the inefficiencies in your steam system without going to complex heat recovery solutions. Again, just let's simplify it a bit further. And we look at the 4 core areas of what is the steam fundamentals of condensate flash recovery, insulation, trapping, and boiler house optimization. And you need to understand where you were on your sustainability journey. So in other words, you shouldn't be looking to go to the complex engineering first. It was mentioned earlier about the low-hanging fruit or more easily addressable projects. So what you need to consider, where you are, if these kind of problems are those which could be, you see familiarity with your own site. Because again, we need to understand the optimization influencers. So in other words, what will influence an efficient system? Again, we talk about, steam dryness, steam quality, etc. And what you're seeing is that for those kind of 4 key areas, that about 41%, which is of savings, can be achieved very easily with simple engineering. So in other words, we can keep away from the production optimization or the pinch heat recovery. Though, although they're attractive, what you should be looking to do is to understand where you are in your journey, and before driving towards, again, what we call complex engineering, address those simple areas or more easily addressable areas, because what you'll find is that a lot of this is in the steam generation and distribution system. So in other words, you don't have to try and optimize the process to get very attractive savings. Let's look at financial terms. So when we consider the different type of opportunities, and we look at what could be considered less than 3 years as an attractive return investment, and this is simple payback, what you can see is that your insulation traps, they're very, very attractive financial incentives. Although you see boiler house optimization, can be expensive, but what we have found is that customers who did engage us with boiler house optimization projects addressed a lot of the fundamental issues in their steam system, So the likes of the separation, effective drainage, the double block and bleed. So they would basically burden the energy efficiency project with what we call system improvements. So that's why this figure tends to be high. However, what you're seeing is that on average, all the projects will give a less than 3-year return on investment. So in other words, these projects are viable and doable within industry. So finally, what we're going to do is that, water is also a key driver for industry. And when you look at the different types of technologies to see is that how you can get to, using water more effectively, the different type of opportunities. And again, what we're seeing is that, about 33% of the total water savings can be achieved, again, very easily within what we call the steam system fundamentals. Reason why HVAC is so high here is that you don't use water within HVAC, but what we have found is that you have refrigeration systems which reject heat energy through cooling towers. Cooling towers use water as a means of evaporation. Hence, that's why we're finding that where, especially in the Asia region, where there is a lot of need for humidification or dehumidification, that's why water demand reductions could be quite significant. Okay. Again, that was just to kind of give you a bit of insight into industry. So, to other words, learn from what has been done with companies that have a more established, say, energy management program. Learn from the kind of opportunities that they have found within their own systems. But more importantly, to recognize that steam efficiency improvements can be achieved with challenging some of the more simplistic aspects of your steam system without having to go into complex process engineering. Those projects will be done in time, but best start with what we call the low-hanging fruit or the more easily addressable fruit. However, let's consider your steam system, and we talk about the 5 pillars of an efficient steam system. So we will talk about the steam production, the impacts to efficient steam generation, high quality steam. We then need to look at how you manage your energy. So you're looking at your condensate recovery rates or your heat exchangers and potential areas. We mentioned about controls. Again, remember the classification of valve is the process on off, whether you're in optimum control or not. Because a lot of times we have found that control is lacking, and the very nature in which a steam valve operates, for example, if it rapidly goes from 0 to 100%, has a big impact on the boiler house. Again, Dave mentioned about the metering. It's important that you visualize your consumption, understand your process profile, and what I mean by that is understand the frequency and amplitude change. So in other words, how quickly your steam demand changes, how much it changes by. So in other words, these are a step change, a gradual change, and the instantaneous change. So in other words, do you find the process goes from 0 to 2 tons of steam and back to 0 very quickly? And we will also be talking about how to recover and transfer your energy. Again, please remember, we mentioned about flash steam generation. It's unavoidable where you have high pressure condensates, but there is means and measures to recover that energy. So again, from our own experience, when you consider what we've identified through our audit process, you can see that realistically, these are the type of savings that can be achieved through the different systems from generation right through to the actual process itself. Now, when we talk about the process itself, we're finding this is where like the waste heat recovery comes in. So for example, you have retorts which may reject a lot of heat to atmosphere. That heat can be recovered, for example, to preheat boiler makeup water, for example. And also when we look at distribution losses, the traps, the vent steam, etc. And again, we will demonstrate how you can recover that energy. So let's start with generation. So you have a boiler, or in reality, you probably have multiple boilers which are supporting your site steam system. You may have a scenario where we have one duty boiler or standby boilers. And what the function of the standby boiler is to ensure that your steam distribution pressure is being maintained at a constant. What we have found from our experience is that the very nature in which you use steam could cause your standby boiler to intermittently start-stop to basically counteract a pressure reduction. So let's look at your steam boilers. So is there enough evaporation at times? What that means is that can the boiler generate the steam at a rate of pace at which it's being consumed? Or do you find that you have what we call steam starvation or pressure decay? What that means is some index users are struggling to achieve temperature if, for example, another process comes on. So in other words, how does your boilers operate in response to matching your pressure? 2, is there enough boiler pressure? So the problem is that if you see that your boiler pressure swings up and down, then you have what you call carryover and end user corrosion. Carryover means is that when you reduce the pressure in the boiler, there's a tendency for the steam within the boiler to start condensing back down. And if you get a high instantaneous demand, you get a high extract velocity, and you end up dragging this water into the system. Also, if we reduce the pressure, which we'll demonstrate in a minute, there's a foam layer on the boiler surface. This foam layer tends to become more erratic, and you're carrying chemicals and water into the steam system. You also need to understand, is there enough condensate return? So we will demonstrate why you should be returning condensate, the financial benefit. But it's not just a case of how it's returned, but how it's brought into the system and how it interacts with your makeup water system and your boilers. Is there proper water treatment? What we have found from experience that a lot of the problems in steam systems is a misunderstanding of the water treatment regime, the impacts it has on the quality of water in the boiler, and effectively, if it's not controlled, can impact even simple things like boiler level controls. And if you've ineffective level control, then you've an inefficient boiler system. However, on a steam distribution system, where there's ineffective treatment, where there's carryover, you end up with corrosion and even blockages of some end users, because you end up bringing particles into the steam distribution system. Okay, is there auto TDS control and blowdown? Often we find that they're installed, but not working effectively. And where there's ineffective TDS control, you end up causing more what we call issues with carryover. Is there heat recovery from TDS, where you have high TDS blowdown because of water quality? Are you recovering that energy? And again, we give a case example. Is the feed water temperature at least 80 to 90 degrees? So if you just use a hot water tank, do you maintain a minimum 80, 90 degrees, or do you have a pressurized deaerator? Because what the purpose of the chemicals in your system is that you want to remove what we call these non-condensable destructive gases, which is oxygen and carbon dioxide from your water. And the best way to remove that is through heat exhaustion, where chemicals are a last resort. So it's, in other words, you need to ensure that your feed water system is at a correct temperature. And then your level controls, is it modulating, is it on or off? And even we have found for customers where they have modulation controls installed, they act in on-off by virtue of the way the boiler responds to the process steam demands. So in other words, load matching and swell. So in other words, how does the boiler operate in response to the process? And a swell is the term given to when there's a rapid depressurization of a boiler. And we're not saying from 10 bar to 2 bar, but you could see from 10 bar to maybe 9 bar or 9.2 bar. But that depressurization causes the water level in the boiler to rise significantly in a very short period of time. And in doing so, you end up dragging water into the steam system at a very point in time where you have high steam demand. So what you want to do is that we need to look at how to achieve an optimal boiler performance, the steam quality, look at how we can reduce life cycle costs, so in other words, financial incentive, and more importantly is that to look at how we can reduce OPEX and maintenance costs, because again, simple investments for energy can improve the effectiveness and reliability of your plant. So let's start looking at what can contribute to an effective boiler system. So again, we mentioned about the flue gas losses, the TDS control, excess oxygen, which was discussed in the introduction. The ability, though, to recover this kind of energy and operate a certain level of excess oxygen will be determined on your fuel source. Where you have natural gas, for example, there is greater ability to recover more energy because it's clean burning. And you can get more of the energy that's entrained in the flue gases because you're not concerned about particulates or fly ash, for example, when burning biomass. So there's different constraints. However, we should be looking at, your TDS control. Are you in control? Are you operating to maybe, cycles of concentration from anywhere from 50 to 100? Because you're an effective system, your TDS blowdown should be less than 1%. In reality, what we're finding can be up to 5% where there's ineffective control. You also have the bottom blowdown. We find that some companies use their bottom blowdown as a means of controlling conductivity in the boiler. This doesn't work effectively. And what you'd find is that you're basically blowing down a lot of water with poor control of TDS control. So it's more effective that the bottom blowdown operates to what it's designed for. And you should only operate it for 3 seconds every 8 hours. The function of the bottom blowdown is simple. The rapid operation of a blowdown valve creates a kinetic internal shock in the boiler to allow you to resuspend settled sludge, where it gets removed more effectively by your surface or your TDS blowdown. It is not designed to control TDS. Also, should be looking at effective feed water control. And although a lot of companies are saying, oh, you should look at feed water modulation control, we're going to be introducing the concept of 2 or 3 element control as a means of counteracting the impacts of on-off process control where you have standard level control and simple things like radiation losses. So in other words, it's a case of looking at all the different factors which contribute to a steam system and understanding where you sit in that process. So again, look at the boiler areas efficiency. So you can find that there's about a 2 to 5% efficiency gain by, in other words, looking at the distribution network. We'll talk about that in more detail in a minute about areas for improvement. It was mentioned about economizers. So you can have what's called a standard economizer, which basically only cools the flue gas temperatures, or you can have a condensing economizer. The condensing economizer uses the latent heat entrained within the flue gases, because in general, your boiler could be about 90% efficient because the latent energy that's contained in the flue gases, which is not used in the standard boiler. Your standard economizer will not recover this energy, it will recover the sensible heat from the flue gases. However, if you have a condensing economizer, which can give you about an 8 to 10% efficiency gain, it's important that you have a cooling medium, which is basically at a temperature lower than the flue gas condensing temperature. So in other words, it's ideal, for example, where you have high makeup water demands in your boiler, that you'd use a condensing economizer because you'll get that high energy input to preheat boiler makeup water. However, it should be understood, especially for the likes of natural gas, is that the condensates which are generated on the flue gas side are acidic. So because of the sulfur content in certain fuels, for example, and the carbon content. So you can carbon dioxide gases, which basically create carbonic acid. And if there's any sulfur content, you create sulfuric acid. So the choice of materials, it means it's expensive. You're using stainless steel grade heat exchangers, but if you have quite a large steam demand, it can be financially attractive. When we talked about feed water modulation control, so it's important to understand is that where you have the control what's employed in the boiler. And often we see where processes are very much on and off, then you could find that your feed water system, although designed for modulation, is also very much on and off. And although you may have a non-condensing economizer, you're not getting the full impact of that economizer unless you have a continuous flow of water through it. What you should be looking to do is get about a 3 to 5% efficiency gain from your non-condensing economizer, but this is only determined by the mode of control of the boiler level water. Again, we talked about TDS designs. So we talk about the feed water quality. So in other words, are you using the right grade water? We should be looking to achieve 2 to 3% efficiency gain by improving the quality of water. If, for example, you have high alkalinity or high silica in your soft water, it may make sense to use reverse osmosis grade water, because in doing so, you could significantly reduce your need for TDS blowdown. Again, you can look at heat recovery. And if you put in heat recovery, you can get anywhere from a 1 to 3% efficiency gain. So again, we should look at both water treatment. Again, look at condensate recovery rates, because condensate is pure water or distilled water. So it's important to basically get condensates returned. But it's also important that you basically get it at a highest temperature possible. So for example, every 6-degree rise in condensate temperature is 1% efficiency gain for your boiler. It was mentioned earlier about excess oxygen and the ability to basically control to acceptable oxygen levels as part of the stoichiometric combustion process. However, please note that certain fuels will demand certain amounts of excess oxygen. So don't be misinformed or misled saying, oh, for my biomass boiler, I can operate to 2.5% excess oxygen or excess O2, because that's what my neighbor who has a natural gas boiler has. So different boiler types, different fuels will have different excess oxygen requirements, but a simple 10% reduction in excess oxygen within the control parameter of your boiler can get over 0.5% of efficiency gain. You can also look at combustion air preheating where there's waste heat. And for a simple 20% degrees increase in combustion air temperature, you can get an additional 1% boiler efficiency. And simple things like the boiler insulation itself. So you could find that your boiler is installed maybe 20 years ago, and although it came with the insulation around the drum, what we have found is that boiler drum insulation sags under its own weight over time. And you could find that although it was designed 20 years ago to give good insulation properties, you may find now that your boiler house has become very warm. It's stuffy, it's hot environment. A simple indicator is that our surface is too hot to touch. Now, I'm not advocating that you go around and start touching everything, but do you feel that there's heat from your surface, your boiler? Use a heat gun, for example, to give an indication of the surface temperature. A good indication of a good boiler house is a cold boiler house. The boiler should not be acting as a large radiator. And we had case examples where we asked companies to remove the old insulation and to reinstall new modern insulation, and in doing so have noticed a marked reduction in temperatures within boiler houses. So in other words, if boiler surfaces are too hot to touch or handle or are indicated hot through a heat gun, there could be financial justification to re-insulate the boiler. Okay, we mentioned earlier about boiler working pressure. So you'll see from this nominal boiler nameplate, you can see that the boiler is designed for 3,000 kgs an hour with a design pressure of 19 bar, but a maximum working pressure of 18 bar. So what you should be doing is that you should be operating your boiler to its design working pressure for two reasons, is that the working pressure will determine the quality of steam within the boiler, because within the boiler, what you're trying to do is the boiler will basically, through addition of heat, create steam bubbles within the boiler water. At design pressure, the steam bubbles are very small. Below design pressure, these steam bubbles grow in size, which means that your water surface, or what we call is your disengaging space in your boiler, becomes very turbulent once a boiler operates below its design pressure. Where it's operating below its design pressure, you could find that you have problems potentially with water level control, because you get this swell effect, which is this movement in boiler water level pending the loads and condition. Also, where the boiler is below its design pressure, the fact you have a more turbulent water surface because it is larger steam bubbles, there's a greater likelihood of what we call carryover because of the velocities of water and the turbulence on the water surface. So in other words, it's better to operate the boiler to design pressure as we recommended in the fundamentals, and then reduce the pressure as required for distribution. Because again, industry has been misled on, reducing pressure saves energy. It may do so in a distribution system, hence we're saying reduce to a distribution pressure. But when we look at the steam tables, the amount of energy required to generate steam, say at 1 bar and 10 bar, the difference is very small. So in other words, you still require practically the same amount of energy to generate steam at one pressure versus another, but the unrecognized problems with steam quality and water dryness in steam system is highly determined on its boiler pressure. Hence, always operate at design pressure to ensure you have high quality steam to end users. So again, understand your system. Now, let's understand. So this kind of video here kind of gives the insight to the boiler. And what you're seeing is that the steam space, or the disengaging space, is this region above the boiler. So you can see is that depending on how the system operates will determine on whether you have a very turbulent system or not. And again, the pressure will determine the foam content around the surface of the water. So what's important to try and control this is that we should be looking at the mode of boiler level control. Because if you employ on-off control, or if you find that your modulation control is acting in on-off condition, each time you add cold water to the boiler, you have the effect of basically rapidly cooling the boiler. Now, you're not seeing your pressure drop from 10 bar to 4 bar, but you could see that your pressure might drop from 10 bar to 9.5 bar each time the pump operates or the valve opens. And again, this has the impact of creating what we call the swell condition and effectively this foaming that's generated on the top of the surface of the boiler water. You should also be looking at, again, your control is in the sense of your blowdown control, your TDS control, because the quality of the water will determine how reactive the water is to basically subtle changes. So in other words, when you have ineffective control, you create high wet steam. And again, wet steam is an insulator. So it's important you have that kind of control in place. Again, we talked about the separation because again, we want to remove this water quality, entrained moisture on generation. Now, when we start looking at your standard on-off control, again, what you will see is that as you start adding in water, you're effectively creating the different working level within the boiler. And the problem is that as the water level changes, the disengaging space changes, which is the surface water level. And where you have high velocity steam extract, you end up dragging water out of the system. And again, what we're finding is that up to 5% efficiency gain can be achieved where you have effective modulation control. So understand your system. So look at your controls. Look what they're saying to you. So for example, this is a representation of a system which basically employed single level control. What you can see is that the process was very much batch driven. And you can see is that they found it very difficult to achieve stability in control. And you can see that the level in the boiler, as represented by the blue line, you can see that the level dropped from a range of 55% to 73%. Even though when you look at the steam profile, which is roughly about 15 tons. So although the steam profile didn't change significantly, what we found is that the subtle changes in the steam pressure causes this swell condition. So where you have single element control, the swell condition forces the boiler to think it's full and stops adding water at a point in time when there's increased steam demand. And if you don't add water to the boiler, you don't get the efficiency of the economizer, for example. So what you should be doing is that as part of your single element control, which is basically looking at the level in the boiler and controlling a valve, you would then add a steam meter on the output. This creates two element control. And what the second element does is that it would then, through a cascade control, look at the level whilst also monitoring the steam consumption. So in other words, it would add water at a proportional rate to the steam being generated as measured by the steam meter within the control parameters of the level probe. And what it does is that if there is a high steam demand and there is a potential for swell, the two element control would basically have different stages in working level So in other words, to allow you to maintain a continuous flow of water into the system. So where your process is batch orientated, or you find you have steam demands is very much on off, as a minimum, you need 2-element control. And again, what we have found that where employed, we have achieved anywhere from a 3 to 5% boiler efficiency gain. Because where it's not employed, we have also found that where you get reduction in pressure, you could find that the second boiler has to fire to maintain the steam demand. So you could find that putting 3-element control means that you can have fate in operating with a single boiler. When we talk about the conductivity in the boiler, and again, you see the foam layer at the top of the boiler. So all boilers have this, and this is purely for demonstration purposes. So unless you're controlling the conductivity in your boiler, there's a greater likelihood this foam is going to be very erratic, and due to the turbulence in the water, you'll find that you end up dragging water into the steam system, which is again an insulator. So it's important that you have continuous TDS blowdown control. Now, boiler manufacturers would recommend certain upper TDS control limits. And what you will find that for a standard boiler, they would recommend, say, 5,000 microsiemens. So in other words, you should control to an upper conductivity of 5,000 microsiemens. However, you should consult with your water specialist because alkalinity or silica or other water properties will determine what your cycles of concentration should be. So in other words, which comes first, the boiler manufacturer's recommendation or the analysis of your feed water from your water specialist? So you could find that although your boiler is designed to operate to 3,000 or 5,000 microsiemens, you may have to reduce the conductivity to control silica, for example, or alkalinity. However, if that is the case, what you should be doing is basically look at the quality of water, see what can be done to improve the quality of water. And if, for example, where you have to control to silica or alkalinity, where you have to increase the frequency or the amount of blowdown, then you should be looking at recovering this energy. Because what we have done for customers is that we would take this high pressure condensate into the flash vessel, which we introduced in the fundamentals, where you would generate flash steam, and you would use the flash energy to basically offset the need for steam in your boiler feed water system, for example. So if in control with high blowdown rates, you need to consider, can you improve your condensate recovery rate? Because if you do so, increasing condensate recovery rates, even by as much as 50%, will represent anywhere from 1% to 1.5% of the fuel saving. Challenge makeup water quality. Just because you have soft water doesn't mean it's the best quality water for your process. Because again, soft water has impurities, and in your boiler, what you're doing is that through evaporation, these impurities retain in the boiler water, where the function of the TDS blowdown is to remove the impurities. So having a higher quality water means less impurities, means less blowdown. So let's consider is that, for example, if you are operating with, say, 200 ppm in boiler feed water, and you were controlling at 2,000 microsiemens, or ppm, sorry, because of silica, for example. In this case, your blowdown rate will be over 11%. So in other words, it's quite a lot of water being lost purely because of controlling to upper parameters, which may be determined by silica or alkalinity. However, if you were to basically looking at increasing the blowdown rate, so for example, that your system is out of control and it's acceptable to go to 3,500 ppm or 5,000 microsiemens. So simply bringing your process back in control means you can go from 11% blowdown rate to 6% blowdown rate at 3,500 ppm. However, if you start looking at, say, changing the feed water quality, say RO water, for example, where you're instead of 200 ppm, you're 50 ppm, you will go from 11% blowdown rate to 2.5% at 2000 microsiemens, or just under 1.5%. So in other words, feed quality of your boiler water is very important. And depending on the quality of your water, in consulting with your water chemist, should mean you should look to see is that what's the best grade water for your application. If you have a high makeup water demand, so in other words, your process consumes a lot of steam, then you should look at potential for basically changing the grade of your water. Okay, so again, improving water quality, reducing alkalinity through reverse osmotic water. You can get up to about a 2% fuel saving. And then finally is heat recovery employed? And this is where Spark Circle can support you, because we have dedicated heat recovery systems. What we would like to advocate what is best for our customers. So the first area of attack is challenge your water quality. If you can challenge it for whatever specific reason, then you look at heat recovery, because it's important to try and reduce the cause of the problem first, and then counteract with how to optimize the waste energy. So that's within the boiler itself. Now let's talk about your boiler feed water system, or your pressurized deaerator, or hot well. We call pressurized deaerators a PDA for short. But it's important to understand the functionality of your feed water system. So is your deaerator or hot well operating as per design specifications? And often we find it's not the case. So you have to start thinking, do you see stability in pressure being maintained? So for example, if your deaerator is designed to operate to 0.3 bar, is it a constant 0.3 bar, or does pressure fluctuate? Is boiler feed water temperature being maintained across all duties? What I mean saying all duties is that your boiler demand, your steam demand. So in other words, are you finding that if the steam demand goes up, you're finding that your boiler feed water temperature reduces? Is the feed water tank or PDA prone to violent shifts, or does it vibrate at times? So in other words, do you find at times there's too much energy, and too much energy means that then you get kinetic energy and it starts vibrating, and you see a lot of losses to atmosphere. And then at times you find it just sits there and it's very quiet. So again, it's understanding how the system operates. Is there a constant invisible steam plume seen from the vent? Because do you find you have too much steam, or you find you have no steam at all? Because the function of the feed tank is to liberate or remove these non-condensable gases, again, oxygen, carbon dioxide, through heat exhaustion. So in other words, you want to remove this these gases through basically heating the water. An indicator is, do you see steam coming out of your vent? And again, it's that what you want to do is to remove your oxygen levels down to ideal conditions, which are in the parts per billion. And if you take analysis of it and you're not, then if oxygen gets into your steam system, it's very corrosive. It is very damaging to steam and condensate system, and is a cause for why you have a lot of system failing. So in other words, a lot of the problems that stem in a steam system come from very poor and ineffective feed water system or deaerator. And what we have found is that where it's not managed, then you're spending a lot of cost in repairing systems. Your system is very problematic, but also, you find us pitting and corrosion, and then your heat transfer efficiency is reduced. And often there's a tendency to overcompensate with a lot of chemicals in the boiler, and all chemicals which are added in the boiler must be removed through TDS blowdown. So in other words, understand your oxygen scavenging. Now, let's take your standard deaerator, and this is just a representation of what Spark Circle would recommend, as part of a package solution. What we're suggesting as a first is for your own process, understand. So look at your level controller. Are you seeing that your level is not constant? Are you seeing that your level is very periodic? You're adding water, on-off control. Look at your pressure on your deaerator. Do you find that the pressure swings up and down? Do you find that the amount of steam that's coming from your vent pipe could be very violent and quite significant, and then drop off quite significantly, sometimes to nothing? look at your steam profile. So look at if there's a steam meter serving the deaerator, look at the profile, because you can see with the trend from this customer is very much on off. And in this case, we found that each time the deaerator filled with makeup water, the second boiler had to start to maintain the steam demand, which is the total steam demand of the system. In reality, it was firing just to satisfy the deaerator, because you could see in this case, the deaerator, the steam demand went up to 8 ton instantaneously, held for a certain period of time and dropped off again. So very much on off. However, look at your even the vent. In this case example, you can see this customer is that each time they filled water into the deaerator, the pressure dropped off significantly because they were surge filling cold water, be it 20 degrees to the deaerator, which had the impact of dousing the water temperature and pressure. And you can see in this case is that the deaerator became sub-atmospheric. So when they were filling water, instead of venting excess oxygen, they were drawing oxygen into the system, which was further impacting on the oxygen content of the feed water. And you can see is that when you add cold water to your boiler, through to cold dumping, or to your deaerator, sorry, due to cold dumping, when you just have on-off control, there's a tendency for the colder water to be dragged to the boiler, even though the mass of water in the deaerator, where your potential probe could say you're at a high temperature. Our own experiences found that where this control is employed, that although your deaerator may say it's 100 degrees, you could measure temperature boiler dropping as low as 55 degrees. And again, the ability of water to retain oxygen is determined on temperature. So again, if oxygen gets into the system, it can cause pitting and corrosion. Again, look at time, retention. So in other words, again, you'll find that depending on the water temperature determines how much oxygen in the system. And what you want to do is get to a scenario here where you're adding water at a proportional rate to consumption. So you have the common or temperature here, or isothermal temperature. So in other words, all the water is at the same temperature, and you're feeding basically aerated water to the boiler. And again, this is a common failing we're finding in steam systems, which has an energy impact. So when you start looking at your non-deaerators, what you should also looking is that if you have what we call a hot well tank, that you should also have what we call the atmospheric deaerator head installed. And the idea here is that you would take your makeup water, your condensate recovery, and through this immersion, through what you would do is that you would basically blend the two streams into each other, such that again, you're creating the isothermal water temperature and you don't have the impact of the cold dumping. If you have a hot well tank where you have cold water coming in one side and condensate on the other side, there's a potential for thermal stratification. And again, you could find significant temperature swings to your boiler water. And again, what we want to do is, improve the quality of boiler feed water such that then you can reduce the demand of chemicals, reduce the demand for blowdown, and help create better quality steam, which is a higher quality steam, more efficient steam use, and more efficient steam system. So let's consider now your distribution system. So what you're trying to do is generate high quality steam. And we spoke about the separation of steam from the boiler. However, your distribution system is quite large. So what you need to consider is that on your distribution system, for your end users, do you have enough pressure? In other words, do you see pressure swings at your some end users? If that's the case, you would have to look at pressure management. So in other words, increase the distribution pressure to compensate, because where there is a certain pressure, a pipe has a certain capacity to carry steam. Increasing the pressure means it can carry more steam more effectively at reduced velocities. So again, what you want to do is reduce the velocities in your system. So you should basically operate at a pressure, whereas that if from your system you have a lot of noise coming from your steam system, it means you're distributing steam at too low a pressure. And where you have high velocities, you have high erosion. Where you have high erosion, you tend to wear down seats on valves, you tend to wear down steam systems, you tend to wear down steam traps, which means then your leaks from failed open traps become higher, or your valves which are meant to be closed can't close because of erosion, you get a hotter leakage steam. So in other words, you want to get your distribution pressure to a point where you have no noise from the system, such that you can reduce your velocity. Again, we talked about mains drainage, the wet steam, eliminate water hammer, leaks. What you'll find is that the quality of steam, which we mentioned earlier about the chemicals and the oxygen, means that if your steam is acidic because there's oxygen in it, you may find you have a lot of leaks in your system. And what you could find is that the reason why you have leaks is, again, by virtue is that the feed water tank or the deaerator is not doing its job. So in other words, where you have indications of leaks in your system, it's because of potentially steam quality. And again, we talk about water hammer, the trap stations. Is there issues of pipe corrosion? Again, water quality, treatment, deaerator operation. Not only you find it may cause traps to fail open, but where you have pipe erosion due to poor water quality, you might find that traps are failed closed. And you could say, oh, a failed trap or closed failed trap doesn't lose energy, but increases the likelihood for water hammer. It retains water in the system. And 1-2 millimeter of water on the heat exchanger can reduce heat transfer efficiency by as much as 10%. So in other words, you could then find that you're using a lot more steam. You have to operate heat exchanger higher pressure. Higher pressure is higher pressure condensates. Higher pressure condensates means higher flash losses at vented condensate recovery systems. So in other words, it has a compounding effect. Again, we talk some things, insulation. Just because insulation was installed 20 years ago, doesn't mean it's best in class now. For exterior applications, is it cladded? Is it protected from water ingress? Is it sagging? Is it wet? Wet condensation or wet insulation is worse than no insulation. So in other words, we should be checked on a continuous basis. And redundant pipework, you should look is that unnecessary heat loss where there was a production area is not in use anymore, isolated. If you don't have an isolation, through a shutdown, put in an isolation valve to allow you to take down the header. And safety valves, what we find is that, you have recommend pressure control, but again, where you have poor quality steam, you may find that the pressure control valves can't achieve optimum control. And you might find that safety valves are starting to leak or pass. And again, indication of an ineffective system. So what we're looking to do is get optimum performance, reduce running costs, and reduce maintenance. And in doing so, you could find that your efficiency of your system will increase significantly. Now, let's start looking at potential areas. So again, we start looking at what was the International Energy Agency, and then we start looking at where the losses are attributed to the system. So we could find that on average, about 6% of your fuel energy is lost through distribution. So multiple case examples where you would see exposed valves. Simple things like this are quite a significant energy loss, act as large radiators. So can easily be addressable by improved efficiency or insulation jackets around valves, for example. So you'll also find steam leaks, for example. If this is a regular occurrence, again, don't just fix the leak in the sense of, yes, that will address your steam leak, but you need to look why your leaks are occurring, which means is that what we call root cause analysis. Look at your water quality, see is it acidic, see are you removing the oxygen, and does the water quality have an impact on the ability of the steam system to basically maintain the self-contained system without loss. Again, we're looking at traps. So we talked about traps that on average a 10% failure rate. So this is what we call the Spark Sarco STS-17. And what it's designed to do is that when you're replacing a trap, we have identified that the biggest issue with replacing traps is the ability to basically work on an individual piece of equipment safely while maintaining a steam system. So this just shows a single isolation, but you can also get a double isolation where you could have 2 isolation valves on the steam side and on the condensate side, and through a bolt connection, you can remove the faulty trap. In other words, you can reduce the downtime required to replace faulty traps. You also look at condensate losses. So simple things like allowing condensate to go to drain. You can see in this scenario here, this is a case example where we're experiencing what we call stall. So in other words, what it did is that the customer is traps that weren't working because of stall in the heat exchanger. The only way he could get the system to operate was to open a manual bleed valve. However, when you open a manual bleed valve, it accounts for, you can't account, sorry, for different process conditions. And what we found here was that at times it was just pure steam coming out of it. And as the process load increased, then you got a lot more condensate. But again, the system here was operating like this because of what we call stall. So in other words, you put in the pump trap to compensate. Then you have your vent steam losses. And if you see here like a vent from a condensate recovery unit, you have a lot of flash steam losses. What you should be doing is conducting a steam trap survey using Spark-Sarco's expertise, because we know exactly where and why the losses are occurring. And if unavoidably, we can then say what can be done. But a good indicator, you have a problem with distribution system if you see a lot of flash steam potentially coming from a condensate recovery unit. So in other words, address the source of the problem. So we talk with steam trapping, again, talking about 5 to 10% failure rate. There should be a need for a scheduled trap population assessment at least once a year. Use external expertise, because this is a specialty in its own right. And you need someone with an engineer or technician with the expertise to understand when traps are working within its design parameters or not. Again, you need to look at how you can act on the findings. And like mentioned with the STS-17 is that instead of just replacing a trap, look at what can be done to simplify future maintenance, because again, best in practices, there's got 5 to 10% annual failure rate. So in other words, there's a likelihood that you might install a trap now, but you may have to go back to it in 10 years' time, for example. Okay, again, look at excessive flash losses as an indicator there's a problem. Failed open traps, create what we call a phantom load. So in other words, you could find your steam demand base load is quite high, and this is easily addressable by just challenging your steam traps. Again, we talked about failed closed traps. It influences water hammer and poor heat transfer efficiency. And again, indication is that where you have a lot of failed open traps, look to see what's venting from your condensate recovery systems, because that is a good indicator there's something wrong in your system. So look for the telltale signs. When we start looking at effective distribution, you could see is that there's two sides to it. That you'd see plenty of cases where you'd have the pipes would be insulated, but isolation valves, whatever, would not be insulated. If you were to look at it with a thermal imaging camera, you could see very quickly the heat that's being radiated from the exposed pipe work. So there's two kind of areas: health and safety. There's a risk of accidental injury, if someone was to come in contact with it. So scalding and burning. But on an energy perspective, you need to consider is that these exposed pipes, not only do they radiate heat to the atmosphere, but you find is that the steam distribution system, in some cases, can be one of the biggest single steam consumers, because although you're serving steam to end user, your distribution system runs 24/7 so long as the steam system is primed. The process may operate on and off, but your steam system is continuous. So what you could also find is that the likes of these valves increase the cause for water hammer, because as you radiate heat, the steam inside here condenses, creating water, and where it's not removed effectively, then you basically increase the likelihood of water hammer damage. You could easily apply what we call these removable insulation jackets, and in doing so, you can eliminate as much as 90% of the standing losses. The benefit these insulation jackets offer is that should you need to do maintenance on the valve, you can remove the insulation jacket through one of your own crafted technicians without the need for specialist insulation companies, so we can ease the maintenance issues. What you'll find as well in the case example here, you could see is that, for steam that was about 10 bar, for example, you could see that the surface temperature would be 180 degrees. Whereas if you use the insulation jacket, you significantly reduce the surface temperature, and you can see quite a dramatic reduction in the energy loss. So in other words, look at the simple things. Do a survey of your steam system. If you find there's case examples of this, do it for basically the financial impact is that you reduce cost, The efficiency is that it doesn't become a steam consumer, you reduce your steam demand, and you're eliminating potential cause for water handling. If you're kind of looking at, you know, a simple likes of steam leaks, there is sizing charts available to see that kind of give you a kind of a financial kind of indication of, you know, the benefit of basically fixing the leak. Because often we're saying is that, oh, we recognize the leak is there, and the customer says, yes, we know it's there, but we need, you know, downtime to fix it. But, you know, simple things like understanding, you know, potential leaks. So you can see is that, you know, as the leaks get worse, which are visible by the size of the plume, you can see is that, you know, even if you got a 1/2 inch size hole, that, you know, you could lose up to about 400 kgs an hour, which is, you know, nearly 48,000 pounds when considered, you know, on UK price of like 2.5 pence per kilowatt hour for gas, for example. So in other words, you should try and address these in, you know, using the size of the plume as justification for senior management that you need the time required to make those repairs because of the financial and energy impact. So when we start looking at condensate recovery, we look at the key drivers. So we look at, you know, water or condensate is pure water because it's distilled water within the boiler itself. We reduce the cost of effluent. So in other words, that if we have to blow down a lot of water as an add makeup water to the system, then we increase the costs of water. Chemicals, boiler concentration, regulation, and safety, all have an impact. If you were to look at the in financial terms, and what we have done here is to look at different fuel sources and the different condensate temperatures, and you can see is that there's quite a significant step change between the, you know, the efficiencies of returning condensate on a financial perspective and an energy perspective. Because if you're going to say like heavy fuel oil, you see there's a greater incentive to recover condensate, and you can see the difference here at this table, basically what it means to your business on basically recovering condensates. Again, when we talk about flash energy, it's the opposite to the boiler. So what you can see is that at atmospheric conditions, water can only hold a certain amount of enthalpy of water. Where you have waters at different pressures or condensates, then you can see, for example, here, that the available energy that is entrained in condensates, which is given up as flash energy, can be quite significant. And depending on the pressure, can be at least 50% of the total energy. So at 10 bar condensate, you will find that the condensate is about 28% of the total enthalpy of steam. However, when you look at what's lost, you could see that about 47% of the energy in that condensate gets rejected to atmosphere, you know, through evaporation, purely because through depressurization, you basically cause high pressure condensates to release its residual energy. In doing so, you will also cause about 13% of the volume of water to be lost as flash steam. So when you start looking at condensate recovery systems, is that best to eliminate the flash steam as source of generation. If it's a centralized condensate recovery system, you should look to see, can you take this flash steam to the boiler house? Can you incorporate it in the boiler feed water? If not, you look at the process that's actually generating it to see, can you use the preheat process makeup water? So for example, you know, we kind of give a case here of a process application, uses 1600 kgs an hour steam at 10 bar. What you do is you put in a flash vessel, and basically you depressurize the condensates. You could even create low pressure steam for end users, or you could even use technology like a thermal compressor where you would basically use the flash steam and recompress it back up to a working temperature. You could also take it into what we call an exhaust vapor condenser. And what you do is that you basically use a cooling medium like process water or boiler makeup water, and basically condensing the flash steam and effectively recovering the energy. So in other words, what this is trying to indicate is that there's no one fit solution. It's to look at your process, your application, and then see what's the best solution to suit your needs. This is where the benefit of audits come in, because through the audit, you identify a solution relative to your own applications. So when we start looking at condensates, why you want to get condensates back is just, for example, is that when you look at 10 bar condensates and you look at feed water at 70 degrees, getting condensate back can reduce your energy demand, your boiler, quite significantly, because the enthalpy of water is quite significant in comparison for boiler feed water at 10 degrees. So in this case, where you're adding makeup water, this is your start point. However, when you're returning condensate, for example, at 70 degrees, you can see your starting point and having to add energy into the system. So in other words, every effort should be made to recover condensates at the highest temperature possible. So let's look at lessons learned. Are your boiler design efficiencies being achieved? What factors contribute to poor performance? Can efficiencies be achieved through controls and automation? Again, just because you have installed hardware doesn't mean it's working effectively. You need to ensure that's performing as intended, achieving optimum control. So, in other words, conduct or condensate recovery survey, identify key opportunity areas. An audit, that's the whole purpose of the audit. So understand your steam and condensate system, understand the limitations of the system, and then understand how you can recover energy. Okay, the audit. Will your audit identify deficiencies? Most likely it will, because our experience has shown, even for large multinational companies, there's a lot of deficiencies in the system, which means there's good opportunity for improvement. Again, what you need to understand is your steam system aligned to best practice. And what we say is target the usual suspects. So start off with the simple engineering. Look at the trapping, look at the insulation, look at how you operate steam, look at the feed water system. Use your own system findings to indicate what you need to do. So in other words, the water quality, for example. So in other words, don't rush into heat recovery, act on the simple fundamentals first, and then when you've exhausted them, look at the heat recovery. So we're back to where we started. So you can see is that, again, 100% of your energy input, and about 55% of your energy output. And you can see is that for a megawatt in, you can see the relative losses which are attributed as per the IEA system. So you can see we're only about generating 750 kilowatts of steam. And you can see is that the losses that are basically accounted for within the process conversion. Now, let's look at the points we discussed. So again, we started for every 1,000 kilowatts in. So your flue gas losses. So you can look at economizers. And again, although a lot of you might have economizers, it's the mode of level control. Whether a condensing economizer makes sense, but again, there's limitations on the need for a condensing medium below the dew point temperature of the fuel. There's limitations with certain fuel types, biomass boilers, for example. Radiation losses, again, we should be looking at insulation. Distribution losses, looking at the insulating those exposed components. The flash losses, look at the recoverable technology, recover that flash energy back into the system. You're looking at condensate losses. We can offer condensate recovery solutions to ensure that your condensate's returned at the highest temperature possible. Looking at your blowdown losses, your TDS control, are you in system? Or are you in control? So put in the hardware that allows you to achieve control with the heat recovery. Then start recovering all this energy, and you can see is that very quickly you can start recovering a lot of the losses which are common fault in the steam system. So instead of having, like in this case, 1,000 kilowatts input, you could find that your fuel input could reduce quite significantly, making the system more efficient. So I know we kind of went through a lot of information at this point, but that's why we introduced the concept that, as a company, we've invested a lot in online training. A lot of this information is there. I would recommend that if you have some, more in-depth questions, it's there freely available to be, used. As a company, we do provide the training and the need and the audit services. So in other words, there is services to help and support you. And from there, I think, Eloise, back to you for the Q&A session, please.
Ray, thank you so much for that. That was, again, a really interesting and useful session with so much detail. So I want to say thank you to everybody for sticking with us. I know we're running a little bit over time, and I will take the time to answer a handful of questions that have come through, and thank you for continually sharing these with us. So Ray, just to, on the steam systems, we might have covered this before, but just to ensure this has been covered, how often should the steam trap surveys be undertaken? What's the recommended frequency?
At least once per year, and at least every 6 months if they're critical applications.
Okay, thank you. How this is one for Carbon Trust actually. In terms of prioritizing these issues, how can we get senior management buy-in to implement energy management or ISO 50001? What's the tips there? Kartik?
Yeah, sure. So well, I would like to go back to one of our slides actually. We were talking about the benefits of energy management system. Can you hear me? Yeah. And we're talking about the benefits of energy management system. So if you can, one of the ways is to ensure that you have a systematic, structured approach, that drives energy culture throughout your organization, effective energy management practices. So of course, there's a top-down approach on top of that, which is complying to regulations. That's an immediate requirement. And also, if you want to look at the enabling benefits that one can get from having a proper energy management system in place, is that it revitalizes your procurement policies, it revitalizes your process of identification for energy efficiency opportunities. You also have to look at having a proper energy measurement system in place. So throughout the process of complying to the energy management system, there are a lot of enabling benefits that are also put in place. So such as energy policies, energy targets in place. So it is a structured framework that accelerates your journey, your energy management journey. So these are the ways through which you can secure management buy-in, both the tangible and the non-tangible benefits that you can derive from it.
Great, thanks, Kartik. This is a good one for Southeast Asia here. So, Ray, can you share if you have any experiences on different types of fuel and their HHV effect on the boiler efficiency and potentially their impact on energy efficiency? This is with bearing in mind that FMB companies and SME companies use different available fuel diesels, and also they use diesel and rice husks. Is it harder to control? Is there any kind of implications of fuel swapping? Do you have any comments on that?
Okay, so I do appreciate that we should be driving towards a sustainable operation. So biomass, renewable technologies. There are limitations, however, in the sense that when it comes to biomass boilers, what you may find for some industries that they still need, say, natural gas, for example, to operate those peak conditions, because biomass boilers by design can't react to surge or peak loads. So in other words, that what we should try to do, and what we're explaining here, is try and create more steady state conditions to allow the biomass boiler, for example, to sustain bigger loads. On the efficiency side, we've talked about excess oxygen. It's determined on the fuel source, and the ability to basically look in a condensing mode or non-condensing mode is determined on the fuel source, because again, biomass fuels, by example, are a dirty burning process. So there's fly ash and particulates where you need good control to remove those contaminants before you can start looking at effective heat recovery, or else you'll end up binding those heat recovery systems. So it can be done, but you will find it gets more complex when you move away from clean burning fuels like gas, for example.
Thanks, Ray, that's great. One further technical question. Should the makeup water be preheated before the hot well? And are vertical, this is a bit of a mouthful, are vertical vacuum DA better than the horizontal pressurized systems?
Okay, so a lot of the function of the deaerator, irrespective of type, is to basically to liberate these destructive gases through heat. So you add heat energy, and what you do then is you exhaust these non-condensable gases. So preheating the water into the system, yes, it is highly advisable because it reduces the steam demand of the system. Now, when you look at the different types of technologies, each type of technology has its own peculiarities. So long as it achieves intent, so we talked about high quality water at a specific temperature, then so you can consider, what's the benefit of one over the other. That it might, down to personal kind of understandings, but in general, so long as it meets intent, then it shouldn't be an issue.
Great, thanks, Ray. And we have so many more really good questions, but I'm afraid we're really running out of time. I don't want to take any more time from you from you today. If I could just ask you to answer one final question from us, that would be very useful. It's if you could just let us know whether you found today's workshop useful, that would be fantastic. We just like to collect some information on your feedback, and I hope from the engagement that we're coming through the questions that it seems like there's been a lot of engagement. While you're voting, I just want to remind you that please do get in touch with Carbon Trust about whether you're interested in working with the UK-ASEAN Energy Efficiency Accelerator and receiving more advice, more technical support. And this is all funded by the UK government. And so this is all, you will receive all this support free of charge through the duration of the programme. So please do reach out. I would just say, as the votes are coming in, I'll just say a few more words about today, mainly thank yous. So I just want to say thank you to all that joined us. We've learned about open access tools that we have to our disposal on the UK-ASEAN LCEP website. We've learned about how we can self-assess ourselves and implement a successful ENMS, energy management system, but most importantly, through the really clear and expert input from Ray, we've learned the fundamentals on steam systems and how utterly important they are to making sure that you run your processes and your factories really efficiently. I want to thank Sarit-Sarco for the huge amounts of expert knowledge, one of the world leading companies, to spare this time to talk to you all today. It's really great. And yeah, I really hope you found today's presentations useful. I encourage you to get in touch with either Carbon Trust or Sarit-Sarco if you want to learn more. Obviously, we can direct some more of your questions and respond to some more of your questions. And I want to also let you know that we will be sharing the recording of this presentation on the website, and we will share the link to the recording, so you can have all of the useful information shared today on a video embedded into our website, and also the link to that video. So just want to say again, a thank you especially to the UK government for introducing the workshop today and obviously funding this work, and Sarit-Sarco one more time, but most importantly you all for joining us today, and I really hope you all have a good remainder of the day and stay healthy, and I hope you have a productive 2021. Thank you all for joining us.